shadow looms beyond the edges of our understanding. The universe is vast, so vast it's almost beyond comprehension. Stars, galaxies, black holes, they're just tiny flickers in an infinite night. Now, something new has awakened, an eye capable of seeing deep into the abyss, revealing truths hidden for eons. The James Webb Space Telescope is more than a machine. It's a gateway to the universe's most terrifying secrets. Its mirror, twice the size of Hubble's, stretches like a cosmic sentinel, ready to uncover what was once invisible. As it peers further back in time, it exposes a universe more immense, more mysterious, more dangerous than we ever imagined. What lies in the depths of space isn't just distant, it's unfathomable. And with JWST, we're only just beginning to glimpse the terrifying truth about the scale of everything we thought we knew. As we prepare to journey millions of light years away to witness this cosmic marvel, let's ground ourselves for a moment. I'm fascinated by the idea of us all watching this from our tiny corner of the universe. Let me know in the comments what time it is where you are and whether you're watching this under sunlight or starlight. And if you're ready for the voyage, hitting that like button and subscribing tells me you're on board. The James Webb Space Telescope, often called JWST, is the most advanced astronomical observatory humanity has ever built. It's the next chapter in our quest to understand the universe, designed to peer deeper into space and further back in time than any telescope before it. Unlike the Hubble Space Telescope, which has been our window into the cosmos since the early 1900s, JWST is crafted to explore mysteries that Hubble simply couldn't reach. The primary difference begins with their design and technology. Hubble operates mostly in the ultraviolet, visible, and near-infrared parts of the electromagnetic spectrum. It's powerful, but it's also relatively small for a space telescope. Its mirror measures just over 8 feet across. This smaller size limits its sensitivity and the detail it can capture when looking at extremely distant or faint objects. JWST, on the other hand, boasts a colossal mirror that stretches 11.5 feet in diameter, more than twice the size of Hubble's. This enormous mirror allows JWST to gather much more light, making it capable of seeing objects that are billions of times fainter than what Hubble could detect. Think about trying to spot a single candle flame from thousands of miles away. JWST's huge mirror is like upgrading from a candle to a lighthouse. Another fundamental difference lies in their placement. Hubble orbits Earth at an altitude of about 600 miles, which has been good enough for many observations, but also means it's sometimes affected by Earth's atmosphere, causing slight distortions. JWST is positioned at the second Lagrange point, known as L2, approximately 1 million miles away from Earth. This position provides a stable environment, minimal interference from Earth's atmosphere, and a cold, dark backdrop essential for observing the faint glow of the universe's earliest galaxies. Temperature regulation is a crucial factor in JWST's design. The telescope's instruments are kept at incredibly low temperatures, around minus 275 degrees Celsius, using a massive sunshield the size of a tennis court. This sunshield blocks out the sun, Earth, and Moon, preventing their heat and light from contaminating the sensitive instruments. Hubble doesn't require such extreme cooling because it observes mostly in ultraviolet and visible wavelengths, which are less affected by thermal noise. Of course, JWST's main mission is to study the universe's most ancient galaxies, star formation in distant nebulae, and the atmospheres of exoplanets. Its advanced infrared capabilities allow it to see through clouds of cosmic dust that often obscure these phenomena in optical light. This means JWST can observe the universe as it was less than 100 million years after the Big Bang, almost closing the gap between the universe's birth and the first light we can currently observe. Hubble, while revolutionary for its time, has limitations in studying the earliest objects due to its spectral range and size. It has provided stunning images and deep insights into galaxy evolution, dark energy, and dark matter, but it can't peer as far into the infrared as JWST. The James Webb Space Telescope is designed to fill those gaps, opening a new era of discovery. In essence, JWST isn't just a smaller, more powerful telescope. It's a leap into the unknown with technology specifically crafted to answer questions that have haunted astronomers for decades. It's like moving from a flashlight in a dark room to a floodlight illuminating an entire universe of secrets waiting to be uncovered. As it unfurls its mirrors and begins its observations, humanity stands on the precipice of revelations that could redefine our understanding of existence itself. The James Webb Space Telescope was launched to serve as humankind's most powerful eye into the cosmos, unveiling secrets hidden for billions of years. Unlike the Hubble Space Telescope, which transformed our understanding of the universe, JWST was designed to push boundaries further, peering deeper, seeing farther, and understanding more profoundly. Its fundamental question was, what is the universe truly like at its earliest moments, and how has it evolved into the vast expanse we observe today? One core reason for deploying JWST was to explore the universe's infancy. Hubble glimpsed back nearly 1 billion years after the Big Bang, but JWST aims to peer even further, closer to the universe's dawn, within the first few 100 million years after its birth. This period is critical because it marks the formation of the first stars and galaxies, cosmic building blocks that set the stage for subsequent evolution. Understanding how these primordial structures formed, how quickly they evolved, and their characteristics requires a space telescope with extraordinary sensitivity and infrared capabilities, both of which JWST possesses. Its infrared sensors are designed to see through cosmic dust and gas that obscure early galaxies, revealing the universe's earliest epochs. Another key goal is to investigate the origins of life by examining exoplanet atmospheres, planets orbiting stars beyond our solar system. Analysing their chemical compositions, scientists hope to identify signs of water, organic molecules, and other life-essential ingredients. The aim isn't just to find planets, but to understand the conditions fostering habitability and potential life elsewhere. This quest raises fundamental questions. Are we alone, or is life common in the universe? By studying distant worlds, JWST seeks to address these profound mysteries, opening new frontiers in astrobiology. The telescope also aims to deepen our understanding of stellar life cycle processes. From their birth in nebulae to their often dramatic deaths as supernovae, stars shape the universe. JWST's advanced infrared imaging allows astronomers to observe these processes in unprecedented detail, especially within dust-enshrouded stellar nurseries. Studying star formation, evolution, and death will help scientists uncover the physics governing stellar development, nucleosynthesis, the formation of heavy elements, and how matter is distributed across galaxies. Beyond stars and planets, JWST was launched to examine the large-scale structure of the universe, including dark matter and dark energy, which influence the universe's expansion and evolution. Despite remaining among cosmology's greatest mysteries, JWST offers vital data to shed light on these components. Its observations contribute to understanding the universe's expansion history, helping refine theories about its ultimate fate. The scientific goals of JWST are interconnected. By uncovering the universe's earliest moments, studying star and planetary system birth and development, and analysing exoplanet habitability, it aims to answer questions that have captivated humanity for centuries. How did the universe begin? When did life emerge? And how widespread might it be? What physical forces shape the cosmos? These inquiries go to the core of our existence, exploring our place in the universe. To achieve these ambitious goals, JWST employs a suite of innovative instruments. Its primary mirror, over 6.5 meters in diameter, collects faint light from the distant universe, surpassing previous space telescopes. Its instruments operate mainly in the infrared spectrum, allowing it to peer through cosmic dust and reveal objects otherwise hidden. This combination of sensitivity, resolution, and wavelength coverage makes JWST uniquely capable of observing the universe's most obscured and distant regions. Launching JWST was a complex effort involving international collaboration. It required a powerful launch vehicle capable of delivering its large, delicate structure into a stable orbit near the second Lagrange point, about 1.5 million kilometers from Earth. This position minimizes interference from our planet's heat and light, enabling JWST to conduct high-precision observations with unmatched clarity. Every aspect of JWST's design and mission underscores its role as a cosmic time machine and explorer. It is set to reconstruct the universe's history, from its obscured beginnings to the present day, revealing a universe far more dynamic, intricate, and breathtaking than previously imagined. Its discoveries will challenge existing theories, spark new questions, and deepen our understanding of the cosmos. JWST's launch was not just about deploying a telescope, but about expanding human knowledge, illuminating dark corners of cosmic history, and moving closer to answering profound questions about creation, existence, and the universe's future. Its groundbreaking capabilities promise to transform our understanding of the universe and our place within it, opening new horizons for science, exploration, and human curiosity. The James Webb Space Telescope's design is revolutionary, crafted to push the boundaries of our understanding of the universe. From its towering structure to its sophisticated instruments, every component has been engineered to gather light in ways once impossible, revealing cosmic phenomena at an unprecedented scale. At its core is a massive primary mirror, a marvel of engineering. Weighing over 6.5 tons and spanning 36 feet in diameter, it's made of 18 hexagonal segments of beryllium. Beryllium was chosen for its stiffness and ability to withstand extreme space temperatures, all while remaining lightweight for launch. The mirror's precise segmented architecture allows it to function as a seamless reflective surface, increasing light collection capabilities beyond previous telescopes, enabling observation of faint, distant galaxies and stars previously out of reach. This large collecting area is essential because the universe's signals are faint. A bigger mirror captures more light, revealing the dim glow of objects billions of light-years away. These faint signals can only be detected with JWST's enormous mirror, which can discern individual photons, tiny units of light, allowing it to peer deeper than ever into space. This capacity lets astronomers study galaxies formed just hundreds of millions of years after the Big Bang, scales once thought unimaginable. However, collecting light is only part of JWST's mission. To understand what it captures, the telescope relies on an advanced suite of instruments, each designed to observe across a broad spectrum, from visible light to mid-infrared. While our eyes see a narrow electromagnetic range, JWST's instruments expand our vision, revealing phenomena obscured or invisible at other wavelengths. One key instrument is NIRCam, near-infrared camera, designed to observe in near-infrared light. Crucially, near-infrared can pass through cosmic dust clouds that often obscure objects. Using NIRCam, JWST can look through dense interstellar dust to study star formation and planet birthplaces. This ability allows scientists to observe regions normally hidden, gaining insights into star and planetary system formation from molecular clouds. Complementing NIRCam is NIRSpec, near-infrared spectrograph, which can break down light from distant objects into component wavelengths. Analyzing the resulting spectra, astronomers determine chemical compositions, temperatures, densities, and motions of celestial bodies billions of light-years away. This detailed data helps us understand how galaxies, stars, and planets evolve across the universe. MIRI, mid-infrared instrument, extends observations into longer infrared wavelengths, allowing detection of thermal emissions from objects too cool or faint to be seen in visible or near-infrared light. MIRI can reveal warm dust around young stars or the atmospheres of exoplanets, providing clues about their composition and habitability potential. JWST's detectors and cooling systems are critical for sensitivity. Infrared instruments must operate at extremely low temperatures, below 270 degrees, to prevent their heat from overwhelming faint signals. To achieve this, JWST has an intricate sunshield made of 5 layers of reflective material, which blocks and dissipates heat from the Sun, Earth, and Moon. The sunshield, roughly the size of a tennis court, acts as a thermal barrier, enabling instruments to operate cryogenically in space's vacuum environment. Positioned at the second Lagrange point, about 145,000 miles from Earth, JWST is placed far enough away from our planet's heat and light interference to operate at peak sensitivity. Its location at this gravitationally stable point also simplifies communication and enables continuous observation of target regions without Earth interference. This stable vantage point, combined with thermal management, allows JWST to collect data reliably over long periods. Deploying JWST was a feat of precision engineering. Unlike ground-based telescopes, it had to unfurl its massive sunshield and precisely align its segmented mirror autonomously after launch, a process taking weeks of delicate adjustments. Once fully deployed and calibrated, JWST is designed for minimal maintenance, promising decades of scientific discoveries. What makes JWST's design truly transformative is how its components work together. Its enormous primary mirror gathers faint light from ancient galaxies, while its advanced instruments analyze different wavelengths, unveiling the universe's hidden beauty and complexity. This synergy allows JWST not only to generate stunning images, but also to decode the faintest signals from early cosmic epochs. Every photon it captures can reveal insights into the universe's infancy, star life cycles, planet formation, and perhaps even the origins of life. Ultimately, JWST's design enables it to explore questions long beyond our reach. It's not just about seeing farther or clearer, it aims to transform our understanding of the universe's origins and future. Every feature and innovation reflects humanity's relentless pursuit of knowledge, crafted to uncover the universe's deepest mysteries and reveal cosmic scales of wonder and awe that challenge perceptions of our place among the stars. The James Webb Space Telescope, JWST, embodies decades of technological innovation, pushing the frontiers of astronomical observation. Its features and instruments are designed to reveal the universe in unprecedented detail, marked by key innovations that herald a new era in space exploration. The primary mirror is a 6.5-meter aperture composed of 16 adjustable beryllium segments. Larger than Hubble's, it gathers more light, enabling JWST to observe faint, distant objects. Beryllium was selected for its stability and thermal resilience. Each segment has actuators that adjust at nanometer precision, ensuring perfect alignment for sharp images across its broad observing range. Constructing such a large mirror posed engineering challenges. It had to be folded for launch aboard the Ariane 5 rocket. Once in space, JWST unfolds through over 100 deployment steps, extending mirror segments, deploying the sunshield layers, and supporting struts. This complex process relies on a network of sensors and actuators working in harmony, showcasing autonomous space hardware capabilities. Another technological achievement is the sunshield, made of 5 ultra-thin Kapton layers coated with aluminum and boron. It reduces solar heat by over 99%, enabling JWST to operate at about -4.5 degrees. Such cooling is crucial for detecting faint infrared signals without interference. The sunshield blocks sunlight and radiates heat into space, maintaining the cryogenic environment needed for sensitive observations. The onboard instruments extend infrared imaging and spectroscopy. The near-infrared camera, NORCAM, employs mercury-cadmium telluride detectors cooled to nearly -400 degrees. These detectors efficiently capture low-light signals, allowing the study of the earliest galaxies formed just hundreds of millions of years after the Big Bang. NIRCam is complemented by the near-infrared spectrograph, JWST, which performs detailed spectral analysis by splitting light into component wavelengths. Using innovative grating technology and precise optics, JWST examines the chemical makeup, temperature, and motion of distant objects, vital for understanding early galaxies, stars, and exoplanet atmospheres. The mid-infrared instrument, MIRI, extends observations to longer infrared wavelengths. It combines an imaging camera and spectrometer, cooled below -375 degrees, with a dedicated cryo cooler. Achieving such low temperatures is challenging, but allows MIRI to penetrate cosmic dust, revealing structures within galaxies, star-forming regions, and distant planetary atmospheres. Pointing accuracy and stability are essential for JWST's observations. Its fine guidance sensor, along with NIRCam and the slitless spectrograph, lock onto faint guide stars, ensuring stability better than half an arc-second. This precision prevents jitters or vibrations that could blur images, enabling highly detailed and reliable observations of faint distant objects. All these innovations, massive foldable mirrors, deployment mechanisms, multi-layered sunshield, advanced detectors, sophisticated spectrographs, and precise pointing systems, combine to create a machine capable of observing deeper into the universe than ever before. This enables exploration of epochs when galaxies first formed, revealing earliest cosmic phases and intricate structures. JWST is more than a telescope. It's an icon of human ingenuity. Designed for discovery, its technological advances surpass previous capabilities, opening new frontiers in astronomy. It allows us to peer back in time, observe galaxy formation, and understand the universe's fabric on an unprecedented level. Each feature and instrument demonstrates a synergy of science and engineering, pushing limits in space exploration and observational astronomy. These innovations do more than advance technology. They expand our ability to explore profound cosmic secrets. From its foldable mirror and cryogenic instruments to its autonomous deployment systems, JWST embodies human achievement and scientific ambition. It will revolutionize astronomy for decades, reshaping our understanding of the cosmos and our place within it. Its groundbreaking innovations exemplify daring leaps that enable us to see galaxies forming and explore the universe's earliest moments. Every feature underscores a significant achievement, merging engineering mastery with scientific vision, steadily expanding possibilities. In doing so, JWST enhances our capacity to unlock cosmic mysteries that have long eluded us. Its innovative mirror design, advanced detectors, and thermal management systems exemplify the pinnacle of technological progress. Autonomous deployment and precise pointing ensure stability and clarity for delicate observations. This combination of engineering mastery and scientific ambition guarantees JWST's profound influence on astronomy. It broadens understanding of the universe's origins, evolution, and complex structures. Its innovations not only advance technology, but also expand human knowledge, allowing exploration of the universe's most profound secrets. In essence, JWST is a testament to human creativity and perseverance. Every component, from its foldable mirror to its cooling systems and autonomous deployment, exemplifies scientific innovation. It pushes observational limits, offering a window into the universe's earliest epochs. These breakthroughs position JWST to revolutionize our cosmic view, opening new frontiers in discovery. The James Webb Space Telescope, JWST, is positioned at the second Lagrange point, L2, about 1 million miles from Earth. This location enables it to peer deep into the universe with exceptional clarity, avoiding the thermal noise and light pollution that hinder observations from our planet. Its stable, cold environment is crucial for capturing the faint signals from the farthest objects, allowing the telescope to reveal the universe's true scale and grandeur. Unlike the Hubble, which operates within Earth's atmosphere, JWST has a massive segmented mirror over 6.5 meters across, more than 2.5 times larger than Hubble's primary mirror. This larger aperture grants it prodigious resolving power, enabling it to gather more light from distant galaxies, stars, and nebulae, and uncover features previously hidden in darkness. JWST's suite of instruments covers a broad range of infrared wavelengths, making it possible to see through cosmic dust and gas that obscure many celestial objects in visible light. Infrared light penetrates dust more effectively than visible light, revealing phenomena within star-forming regions, galactic cores, and the early universe, opening a window into times and places unattainable before. Its cutting-edge technology enhances its ability to measure the universe's scale. Sensitive detectors record minuscule fluctuations in faint signals, and its ultra-precise pointing system keeps it steady and accurately locked onto targets. These innovations ensure JWST collects data with exceptional clarity, allowing astronomers to reinterpret distant observations in ways impossible before. JWST's launch and deployment involved remarkable engineering, settling into orbit at L2 and unfolding its 5-layer sunshield, which maintains instruments at around -400°. This cooling is vital because the telescope's own heat could drown out the faint light from distant objects. Passively keeping the instruments frigid allows JWST to perform optimal infrared observations, revealing the universe's grand architecture in exquisite detail. A key feature of JWST's ability to uncover the universe's scale is its capacity to look back in time. Because light takes time to travel across space, observing distant galaxies means peering billions of years into the past. By detecting faint, distant signals, JWST captures snapshots of the early universe, some just hundreds of millions of years after the Big Bang. These observations challenge previous theories about galaxy formation and evolution, prompting scientists to revisit the cosmic timeline. More than just seeing distant objects, JWST helps us understand how the universe's structure developed, from tiny primordial fluctuations in the cosmic microwave background to the vast web of galaxies we see today. Its ability to probe the universe's infancy aids in mapping the colossal web of matter that spans billions of light years, emphasizing the vastness of cosmic architecture. JWST also detects the faint glow of primordial galaxies and the diffuse filaments of dark matter, the mysterious, invisible substance constituting most of the universe's mass. By studying how light from distant galaxies is bent and magnified by these unseen structures, scientists begin to map the universe's large-scale framework, revealing just how vast and interconnected the cosmos is. In addition, JWST shines a light on the life cycle of stars and the formation of planets. Observations of stellar nurseries, clouds of gas and dust where stars ignite, illustrate the monumental scale of these processes. The countless stars forming simultaneously across numerous galaxies portray a universe teeming with activity, growth, and change on a staggering scale. The telescope's inward gaze also includes exoplanets, analysing their atmospheres for signs of habitability. While seemingly localised, this capability underscores JWST's immense reach. From identifying molecules in distant atmospheres to tracing the evolution of massive galaxy clusters, JWST's broad survey capacity spans multiple layers of cosmic scale. All these technological and observational achievements assemble into a narrative. The universe is unimaginably vast, layered in complexity, and far older than previously believed. JWST has pulled back the curtain, revealing a universe full of wonder, filled with structures that stretch human comprehension. It's like being given a cosmic ruler and high-definition glasses, enabling us to perceive the universe's true grandeur in ways that make past observations seem limited. This is just the beginning. As JWST continues collecting data, it promises to reshape our understanding of cosmic scale, illuminating mysteries that have puzzled humanity for centuries. The scope of the cosmos is now fully revealed, limitless, magnificent, and immense. It reminds us that we are mere tiny specks in an expansive universe that has been unfolding for billions of years. With JWST, we're finally beginning to see its full magnitude, revealing a universe of astonishing size and complexity. The James Webb Space Telescope is equipped with a sophisticated suite of instruments, each meticulously designed to unlock different secrets of the universe. These instruments work together to provide a comprehensive view of cosmic phenomena, from the formation of the earliest galaxies to the atmospheres of distant exoplanets. Let's delve into the main instruments on board the JWST and explore their specific functions. First, there's the Near-Infrared Camera, or NIRCam. NIRCam is the prime instrument for capturing high-resolution images in the near-infrared spectrum. It covers wavelengths from about 1000 nanometers to 2.5 microns. This allows it to peer through cosmic dust clouds that often obscure objects in visible light, revealing hidden star nurseries and the faint glow of the universe's first galaxies. NIRCam's exceptional sensitivity and wide field of view make it perfect for conducting large surveys of distant objects. Its ability to detect faint signals helps scientists study how stars and galaxies formed in the universe's infancy, providing clues about the evolution of cosmic structures over billions of years. Next up is the Near-Infrared Spectrograph, or NIR spec. Think of NIR-spec as a cosmic decoder. Its purpose is to analyze the light from celestial objects and break it down into spectra, allowing scientists to determine the composition, temperature, density, and motion of distant galaxies, stars, and exoplanets. NIR-spec is unique because it can observe up to 100 objects simultaneously with its multi-object spectroscopy mode. This incredible efficiency means astronomers can gather data on numerous targets in a single observation, vastly speeding up the process of understanding the universe's building blocks. Its spectral capabilities are crucial for studying how galaxies formed and evolved, how stars are born, and even for characterizing the atmospheres of exoplanets, potentially revealing clues about habitability. Complementing NIRCam and NIR-spec is the Mid-Infrared Instrument, or MIRI. MIRI extends JWST's observational reach into the mid-infrared spectrum, covering wavelengths from about 5 to 25 microns. Why is this important? Because many key cosmic processes emit strongly in the mid-infrared. MIRI can detect warm dust clouds heated by star formation, uncover obscured galaxies hidden behind thick veils of cosmic dust, and study the atmospheres of planets both within and outside our solar system. Its capabilities shed light on the life cycle of stars, from their birth in dense nebulae to their death as supernovae. MIRI also provides detailed images and spectra that help scientists understand the distribution of organic molecules and other complex compounds in space, bringing us closer to understanding the origins of life itself. Lastly, we have the Fine Guidance Sensor, or FGS, which may sound less glamorous, but is absolutely essential. While it's primarily designed for precise pointing and stability of the telescope, FGS also functions as a science instrument in its own right. Its main role is to keep JWST locked onto its targets with pinpoint accuracy, ensuring that the imaging and spectroscopic data collected are sharp and precise. This is no small feat. JWST is capturing faint signals from billions of light-years away, so even tiny misalignments could distort the data. FGS ensures the telescope remains perfectly aligned, enabling scientists to trust the accuracy of their observations. Beyond these primary instruments, JWST also has sophisticated cooling systems and filters to optimize its performance across various wavelengths. The detectors themselves are built with high sensitivity and low noise, essential for capturing the faintest signals from the distant universe. Each instrument is housed in a carefully controlled environment to ensure it functions flawlessly in the harsh conditions of space. Together, these instruments form a powerhouse of observational capability. NIRCam provides stunning images and initial surveys, bringing the universe's earliest structures into focus. NIRSpec allows detailed spectroscopic analysis, revealing the physical properties and chemical makeup of cosmic objects, while MIRI extends the reach into the mid-infrared, uncovering hidden phenomena obscured in other wavelengths. Meanwhile, FGS keeps everything steady, guiding the telescope through the vast darkness with unerring precision. This incredible combination of tools transforms the JWST from a mere observing platform into a cosmic detective. Each instrument's data feeds into a larger story, a story of cosmic origins, evolution, and perhaps even the emergence of life. The insights gained from these instruments will reshape our understanding of the universe, showing us that the cosmos is not only vast, but also filled with continuous surprises and hidden marvels waiting to be unveiled. As JWST peers deeper and clearer than any telescope before it, its instruments promise to reveal regions of space and time that have remained shrouded in mystery for billions of years. With each observation, we come closer to uncovering the true nature of our universe, even if that truth includes a little bit of terrifying, awe-inspiring scale. The James Webb Space Telescope's incredible ability to observe in the infrared spectrum isn't just a technical marvel, it's a doorway to the universe's deepest, most ancient secrets. When we look out into space with visible light, we're seeing a slice of the cosmos that's relatively recent, photons that have journeyed for millions or billions of years to reach us. But much of the universe's earliest history is tucked away beyond that visible horizon, cloaked in cosmic dust and stretched out in the long, red-shifted wavelengths of infrared light. Infrared observation opens a new window by allowing JWST to peer through this dust and see objects that optical telescopes simply can't detect. When the first galaxies flickered into existence over 13 billion years ago, their light had to travel across the expanding universe. During this journey, the universe's expansion stretched that ancient light, shifting it from ultraviolet and visible wavelengths into the infrared. So, what we see in the infrared today is effectively a time capsule, glimpses of galaxies and stars when the universe was still in its infancy, just a few 100 million years after the Big Bang. Imagine looking through a foggy mirror that distorts but also reveals hidden worlds behind the haze. That's what infrared telescopes do. They cut through the cosmic fog of gas and dust, illuminating regions that optical telescopes would see as dark or obscured. This ability is crucial for studying stellar nurseries where stars are born enshrouded in thick cocoon of gas and dust. Infrared light can pierce these shrouds, revealing the processes that give rise to new stars long before they become visible to other means. JWST's sensitive instruments can trace the earliest phases of star formation in distant galaxies, giving scientists a front-row seat to how the cosmos constructed the building blocks of planets, life, and eventually us. Because the universe is stretching and expanding over time, the light from these ancient objects is significantly redshifted. The more distant an object, the more its light shifts toward the infrared. Without infrared observation, we'd be blind to the very edges of the universe's history, the moments when the first galaxies started to form, fuse, and glow in the darkness. JWST's infrared tools enable astronomers to look back over 13 billion years, catching glimpses of the universe when it was less than 1 billion years old. It's like rewinding the cosmic clock, seeing the universe's earliest chapters unfold before our eyes. This ability to see that far back is transformative because it helps answer fundamental questions. When did the first stars ignite? How did the first galaxies assemble? What kind of conditions led to the birth of planets and eventually life itself? By capturing the faint infrared glow of these primordial objects, JWST gives us data that was utterly unreachable before. It's peeling back the layers of cosmic history, revealing how structures evolved from simple hydrogen and helium gas clouds into the incredible diversity of galaxies and stars we observe today. In addition, JWST's infrared capabilities help detect faint signals from the atmospheres of distant exoplanets, some of which orbit stars in young, forming galaxies. This means that beyond just understanding the universe's origins, JWST is also poised to explore the potential for life elsewhere. By analysing exoplanet atmospheres in the infrared, scientists can look for chemical signatures, like water vapour, methane or oxygen, that could hint at habitable conditions or even biological activity. Moreover, infrared observation improves our ability to study the universe's large-scale structure. The distribution, clustering, and evolution of galaxies across cosmic time tell a story about dark matter and dark energy, the mysterious components that govern the universe's expansion. Infrared data allows us to map these patterns in unprecedented detail, setting the stage for breakthroughs in understanding the fundamental forces shaping everything we see. In essence, JWST's infrared eye doesn't just extend our vision, it revolutionizes it. It turns back the cosmic clock, revealing the universe's earliest moments, the birthplaces of stars and planets, and even potential signs of life. It's like having a time machine that takes us directly into the universe's youth, showing us the raw, formative processes that sculpted the cosmos into the sprawling tapestry we observe today. With each discovery, we come closer to answering the profound questions about where we came from and what the universe truly is, all thanks to the power of infrared light and JWST's unprecedented ability to capture it. The James Webb Space Telescope, JWST, is one of the most ambitious and complex observational platforms ever built, aiming to unlock secrets of the universe's earliest galaxies, stars, and exoplanets. In its quest to peer across cosmic distances, it faces numerous formidable challenges demanding innovative solutions, meticulous planning, and advanced engineering for mitigation. These challenges include thermal management, deployment precision, communication constraints, contamination control, radiation exposure, and long-term operational stability. A primary challenge is maintaining its extremely cold operating temperature necessary for infrared observations. Because JWST detects faint heat signals from distant objects, even minor heat contamination from the Sun, Earth, or the spacecraft can obscure data. Positioned at the second Lagrange point, L2, about 1.5 million kilometers from Earth, JWST benefits from a stable position with minimal fuel use for station keeping. Its expansive sunshield, comparable in size to a tennis court, is a 5-layer kite-shaped membrane that acts like an enormous parasol, blocking heat from the Sun and Earth, reflecting and radiating excess heat into space. This layered shield dissipates solar radiation efficiently, enabling instruments to operate at around 270 ding, nearing absolute zero. Achieving such thermal stability required precision engineering to ensure proper tensioning and orientation during deployment. Deployment was another significant challenge. During launch, JWST's primary mirror, composed of 18 hexagonal beryllium segments, was folded to fit within the rocket fairing. Once in space, these mirror segments, sunshield and instruments had to be unfurled, aligned and calibrated with extraordinary precision. The mirror segments contain hundreds of tiny actuators, allowing automatic adjustments at the sub-micron level, ensuring perfect optical alignment despite the distances involved. Months-long deployment and fine-tuning involved automated and remote procedures requiring flawless execution. Any misalignment could have compromised imaging accuracy. Engineers developed sophisticated algorithms and sensors to monitor and correct the mirror's shape and focus, confirming the success of one of the most complex deployment sequences ever attempted in space. JWST's communication with ground control also posed obstacles due to its remote location. At L2, there is a communication latency of about 12.5 minutes each way, making real-time operation impossible. Instead, JWST relies on autonomous systems to diagnose issues and respond promptly, executing pre-programmed routines to ensure safety and functionality. To mitigate potential system failures, onboard redundancy was incorporated into critical subsystems, including power, thermal control, and data handling. Software routines capable of diagnosing faults and executing corrective actions are embedded in its operational architecture. This autonomy is vital for maintaining continual science observations without direct real-time intervention from Earth, especially given the limited bandwidth. Contamination was another challenge, as JWST's instruments are extraordinarily sensitive. Microscopic particles or residual gases on the mirrors can significantly degrade image quality. To prevent this, JWST was assembled and tested in ultra-clean environments, following stringent contamination control protocols during construction and integration. Once in space, protective covers shielded sensitive components until systems were verified to be contamination-free. During deployment, venting procedures and protective covers were employed to prevent dust, debris, or residual manufacturing materials from settling on the optics, ensuring the telescope's pristine observational capabilities over its mission lifespan. The space environment presents additional challenges, notably radiation exposure. Cosmic rays and solar radiation can damage electronics and impair instruments. To counteract this, JWST employs radiation-hardened components and shielding materials designed for a harsh environment. Its position at L2, outside Earth's Van Allen belts, minimizes exposure to high radiation zones, helping ensure electronics longevity. Continuous monitoring and calibration are necessary to detect and compensate for radiation-induced effects that could degrade image quality or cause malfunctions over time. Long-term operational stability was also crucial. While L2 offers remarkable environmental stability, success depends on precise pointing, thermal stability, and reliable power. JWST's sophisticated star trackers, gyroscopes, and reaction wheels enable precise targeting of distant objects. Its solar arrays generate power, and batteries store energy during eclipses. Ongoing calibration, software updates, and autonomous fault recovery protocols are essential for maintaining optimal performance over an expected lifespan of at least 10 years, possibly longer with careful management. In sum, JWST's journey into space involves overcoming formidable challenges through cutting-edge engineering, rigorous testing, and innovative solutions. From thermal management and deployment accuracy to autonomous operation, contamination prevention, radiation shielding, and system longevity, every aspect is meticulously engineered to ensure success. These efforts highlight human ingenuity and resilience as we push the limits of exploration, revealing the universe's profound secrets and vastness. The James Webb Space Telescope doesn't operate in isolation. It forms a vital part of a global network of astronomical observatories, each with their unique strengths, working together to unravel the universe's deepest secrets. Collaboration isn't just a buzzword here, it's a necessity. The combined data from multiple telescopes across different wavelengths creates a richer, more complete picture of cosmic phenomena than any single instrument could achieve on its own. Take, for example, its partnership with the Hubble Space Telescope. Despite Hubble's age, it continues to produce stunning images in the visible and ultraviolet spectrums that complement JWST's infrared focus. Together they offer a layered perspective. Hubble captures the glow of nearby stars, stunning galaxy details, and ultraviolet insights into hot young star-forming regions, while JWST peers through dust clouds to unveil the hidden processes of star birth and galaxy formation deep in the cosmos. By comparing data from both, scientists can generate more comprehensive models, revealing how stars and galaxies evolved over billions of years. But the collaboration stretches beyond just Hubble. The Atacama Large Millimeter Sub-Millimeter Array in Chile, for instance, observes the cold universe, dust, molecules, and gas clouds that are invisible to optical telescopes. When combined with JWST's infrared vision, researchers can trace the life cycle of cosmic material from the earliest star-forming regions to the more mature structures in the universe. This synergy allows scientists to understand how the raw ingredients of planets and life itself assemble in the grand cosmic ballet. Ground-based observatories also play a key role. The Very Large Telescope in Chile provides optical and near-infrared observations that, when paired with JWST data, sharpen our understanding of distant galaxies and exoplanets. Synchronizing observations between JWST and the VLT enables astronomers to track phenomena like supernova explosions, variable stars, and potential habitable exoplanets more precisely. Coordinated observing runs, where multiple telescopes target the same object simultaneously, maximize data richness, minimize ambiguities, and enhance the scientific return. Launch and operational data from space agencies like NASA, ESA, the European Space Agency, and CSA, the Canadian Space Agency, ensure JWST's findings are integrated into a wider scientific framework. Sharing of calibration data, software tools, and analytical models makes it easier for researchers worldwide to interpret JWST's results within the context of existing knowledge. These agencies also facilitate global collaborations, workshops, and conferences that foster cross-disciplinary ideas, driving forward our understanding of the universe. Astronomers also rely on other specialized observatories, such as X-ray telescopes like Chandra and the European Space Agency's XMM Newton. While JWST excels at infrared observations, these X-ray observatories probe the universe's most energetic regions: black holes, neutron stars, and supernova remnants. When the populations of high-energy phenomena are studied alongside JWST's infrared data, scientists can piece together the life cycles of stars, the growth of black holes within galaxies, and the processes shaping the cosmos across all energy scales. In the era of multi-messenger astronomy, JWST is often part of concerted efforts to coordinate observations during transient cosmic events, like neutron star mergers or gamma-ray bursts. Telescopes around the world and in space work in concert, rapidly sharing data and pointing their instruments toward the same targets. This collaborative approach ensures that every bit of information, be it light, gravitational waves, or neutrinos, is captured and woven into a comprehensive narrative. All these collaborations are more than just practical partnerships. They are digital and intellectual bridges connecting scientists, engineers, and institutions across the planet. They amplify our ability to explore the cosmos, turning isolated glimpses into a coherent universe story that spans space and time. When JWST peeks into the distant, dust-shrouded corners of the universe, it's often on the shoulders of many other observatories sharing their vantage points, data, and insights. This collective effort accelerates discovery, leading us closer to answers about our origins, our place in the universe, and the fundamental processes that sculpt reality itself. Every intricate detail of the James Webb Space Telescope's design serves a purpose, and nowhere is this more evident than in its mirrors and instruments. It's a marvel of precision engineering, crafted to unlock secrets of the universe that have eluded us for centuries. The success of JWST's groundbreaking observations hinges on how flawlessly these components work together, pushing the boundaries of what's scientifically possible. The telescope's primary mirror, with its sweeping diameter of 6.5 meters, is composed of 18 hexagonal segments, each made from beryllium, a metal chosen for its stability and lightweight in the cold vacuum of space. These segments aren't just assembled, they're precisely polished to within nanometer tolerances, meaning they are incredibly smooth and perfectly shaped. This meticulous craftsmanship ensures that the mirror can focus incoming infrared light from distant stars and galaxies with astonishing clarity. Even the slightest imperfection could cause blurring or distortions, muddying the data and potentially missing crucial details about the universe's earliest moments. But crafting the mirrors was only half the battle. Once assembled, each segment underwent an intricate process called wavefront sensing and control, which utilized tiny actuators behind the mirror surfaces. These actuators can subtly adjust the position and shape of each segment in fractions of a millimeter. Think of it like tuning a musical instrument, but on a cosmic scale. Small tweaks produce a perfectly aligned mirror surface. This alignment ensures that all light waves arriving at the telescope converge precisely at the focal point, sharpening the images and allowing JWST to detect faint, distant objects with incredible detail. The importance of this precise alignment becomes especially clear when observing galaxies billions of light-years away. At such distances, the light reaching JWST carries vital clues about the universe's infancy. Any blurring or misalignment could mean missing out on critical information about how these primordial structures formed and evolved. Through its adaptive optics, JWST can compensate for tiny errors, providing sharp, high-contrast images that rival the finest ground-based telescopes, but without atmospheric interference. The instruments onboard JWST are equally a feat of precision engineering. Each instrument, like NIRCam near-infrared camera, NIRSPEC near-infrared spectrograph, MIRI, mid-infrared instrument, and FGS-NIRIS, fine guidance sensor near-infrared imager and slitless spectrograph, is engineered for maximum sensitivity and accuracy. Their detectors are built to pick up exquisitely faint signals from the farthest reaches of the cosmos, with noise reduction systems finely tuned to minimize interference. Achieving this level of sensitivity demands components that are not only high in quality, but also impeccably calibrated. Take NIRSpec, for instance. It's capable of simultaneously analyzing the light from hundreds of distant galaxies in exquisite detail, revealing their chemical compositions, motions, and ages. To do this, it must isolate and measure specific wavelengths of light with absolute precision, no room for error. The instrument's incredibly stable optics, combined with thermomechanical controls that keep everything at ultra-constant temperatures, eliminate distortions and drifts that could compromise measurements. Similarly, MIRI operates at cryogenic temperatures, around -250 degrees Celsius, to detect mid-infrared wavelengths. Maintaining such low temperatures in space requires specialized cooling systems and precision thermal controls. Any fluctuation could cause signal noise, drowning out the faint signals from the early universe. The engineering behind these cooling systems is so refined that they keep the instrument stable and perform at peak efficiency over years of operation. And then there's the fine guidance system, like JWST's eye, constantly locking onto stars to keep the telescope perfectly pointed. This system's microscale precision ensures that during long exposure observations, images don't drift or blur. The ability to maintain such stability over hours or even days unlocks unprecedented opportunities for deep field imaging and spectroscopy. All of this precision engineering doesn't just produce spectacular images or data. It transforms raw signals into insights, detailed spectra, accurate measurements of distances, compositions and motions, allowing scientists to piece together the universe's story with clarity and confidence. It's the difference between missing faint whispers of the cosmos or hearing them loud and clear. Every component's meticulous design and calibration mean that JWST can push further into the cosmos than any telescope before it, revealing the universe's true scale in ways that once seemed impossible. As we peer deeper into space, these marvels of engineering ensure that the stories of stars, galaxies, and cosmic evolution are rendered with unprecedented detail, turning the faintest signals into a profound understanding of our universe's terrifying, breathtaking vastness. The James Webb Space Telescope has revolutionized our understanding of the universe's infancy, revealing a landscape more complex and astonishing than previously thought. Even in its early missions, JWST has captured images and data that push the boundaries of cosmic history, shedding light on galaxies forming just a few 100 million years after the Big Bang. Looking back nearly 13.8 billion years, our universe's age, finding the earliest galaxies is like searching for flickering stars in cosmic dust. JWST's advanced infrared abilities allow it to peer through this haze, unveiling structures so distant that their light has taken nearly the universe's entire age to reach us. These observations are rewriting galaxy formation narratives, showing that the universe was teeming with early galaxies far sooner than models predicted. One key discovery involves galaxies forming in just hundreds of millions of years after the Big Bang. Unlike today's mature galaxies, these early structures are surprisingly small, less than 10,000 light-years across, about a tenth the size of our Milky Way. Despite their modest size, they are packed with young hot stars that shine fiercely, making these galaxies detectable across billions of light-years. What surprises astronomers is the rapid assembly of their mass, indicating galaxy formation kicked into high gear surprisingly early. JWST has also uncovered galaxies with complex structures, challenging earlier assumptions that early galaxies were simple and irregular. Many display organized features, spiral arms, dense cores, and interactions with neighbors, indicating galaxy assembly was more dynamic and sophisticated than previously believed. Some early galaxies already exhibit signs of mature morphology, revealing that processes like mergers and gas accretion started almost immediately after the universe's first moments. The telescope's spectral data has shown many distant galaxies are rich in ingredients necessary for star formation: cold molecular gas, dust, and heavy elements. This was startling because earlier models suggested it takes hundreds of millions of years for the universe to produce and disperse these metals through supernova explosions. Finding them so early implies the first star generation formed quickly, enriching galaxies with metals and setting the stage for cosmic ecosystems that developed later. Perhaps most striking is the discovery of galaxies more massive than expected at such early stages. Prevailing theories predicted a gradual build-up of galaxy mass, but JWST shows some already contain hundreds of millions, even billions of stars. This rapid accumulation suggests extremely efficient growth processes, possibly driven by dense dark matter regions pulling in vast gas amounts and igniting star formation at a furious pace right after the universe's birth. This early galaxy data raises questions about cosmic reionization, the epoch when the universe's neutral hydrogen was ionized by the first luminous sources. JWST has identified numerous young star-forming galaxies potentially responsible for reionization. Their strong ultraviolet light suggests these tiny but numerous galaxies played a key role in clearing the cosmic fog, making the universe transparent to light for the first time. All these discoveries point to a universe far more active, rapid, and structured than previously revealed by older telescopes. Early galaxies are not just isolated clumps, they're dynamic systems exhibiting signs of maturity even at the universe's dawn. These findings force astronomers to rethink cosmic evolution models. The timeline for galaxy formation appears compressed, indicating the universe was more efficient at building stars and galaxies in its infancy than once believed. Beyond galaxy evolution, JWST's findings impact our understanding of the initial conditions for supermassive black hole formation and the cosmic web. The presence of mature-like galaxies shortly after the Big Bang implies processes leading to black hole seed formation. Some of the earliest, most massive black holes may have begun earlier and grown faster than expected. These early black holes could influence their host galaxies' growth, contributing to the complex matter-energy interactions observed today. As more data flows in, the picture of the earliest universe becomes clearer and humbling. JWST's insights fill gaps in our cosmic timeline and are transforming our understanding of how structures formed, grew, and evolved in the universe's first moments. It's akin to peering through a cosmic time machine, witnessing birth pangs and early adolescence. The revelations about primordial galaxies do more than deepen curiosity. They reshape cosmological models. They prompt scientists to refine understanding, incorporate new physics, and explore uncharted territory. Each galaxy is a puzzle piece, revealing that the universe's dawn was more vibrant, rapid, and complex than ever imagined. The earliest universe was already bustling with activity, a remarkably swift onset of cosmic evolution that set the stage for the universe today. As the James Webb Space Telescope begins to send back its first images and data, a new chapter in our understanding of the universe unfolds. These observations don't just add details to our cosmic map, they shake the very foundations of our current models of cosmic evolution. For decades, scientists have relied on the lambda cold dark matter model, or lambda CDM, as the best explanation for the universe's origin and structure. It describes a universe born hot and dense, expanding and cooling, with dark energy driving accelerated expansion and dark matter scaffolding galaxy formation. But as Webb peers deeper into space and further back in time, questions arise, some straightforward, some profound, that test the limits of this model. One of Webb's most startling revelations is the discovery of galaxies that appear remarkably mature, with complex structures, well-formed stars and substantial masses, all less than 1 billion years after the Big Bang. Previously, telescopes hinted at rapid galaxy formation, but Webb's sensitivity vividly reveals these galaxies more clearly. Some of them seem to have formed far earlier and more quickly than models predict. This challenges the idea that galaxy formation is slow and gradual, driven solely by matter accumulation over time. Instead, it suggests the early universe was more dynamic, perhaps with processes that accelerated galaxy assembly, or mechanisms not yet fully understood. Webb's infrared imaging uncovers galaxies with unexpectedly high star formation rates. These stellar nurseries are among the brightest objects in the early universe, indicating bursts of star creation on shorter timescales and with greater intensity than models accounted for. If early galaxies formed stars so rapidly, it hints that the universe was a more turbulent evolving environment, with dense gas pockets collapsing into stars faster than expected. This could mean the epoch of reionization, previously thought quick was more complex, involving rapid, localized episodes of star formation that dramatically reshaped their surroundings. Additionally, the discovery of massive mature galaxies at redshifts where models predicted only small proto-galaxies or precursors challenges current understanding. How could these systems have assembled so quickly? This compels reconsideration of dark matter halos pulling in gas and nurturing growth. Was dark matter more concentrated or behaved differently in the early universe? Or did unseen processes, perhaps involving exotic physics, accelerate mass accumulation? These questions challenge core assumptions underlying current galaxy formation models. Webb's spectroscopic data also fuels debate. By examining chemical compositions, scientists find elements heavier than hydrogen, and helium are more prevalent in some early galaxies than expected. This suggests star formation and stellar processes may have been more efficient from the start, leading to earlier, richer cosmic enrichment. Our understanding of stellar evolution, nuclear synthesis, and element formation, the foundation of the lambda-CDM model, is now under scrutiny. These observations support some aspects of existing models, such as rapid universe expansion and dark energy's influence, but also reveal significant gaps and uncertainties. The universe appears more complex, chaotic, and nuanced than our models suggest. Webb's detailed view of early cosmic history paints a picture where regions experienced accelerated growth, unexpected element abundances, and rapid galaxy formation under different conditions than previously thought. These revelations remind us how much remains unknown. Every new data point fits into the cosmic puzzle, but also raises fresh questions. Why did mature galaxies form so early? What triggered rapid starbursts? Are our assumptions about dark matter and dark energy correct, or must they be revised? Could entirely new physics, perhaps involving gravity or matter, alter our understanding of the universe at a fundamental level? As Webb explores further into cosmic depths, our theories will be challenged. These observations don't just confirm models, they compel us to refine, rethink, and even revolutionize our understanding of the universe's grand story. They bring us closer to understanding not only how the universe looked billions of years ago, but also why it evolved into the vast, intricate cosmos we observe today. The first stars to ignite in the universe are among the most elusive objects JWST is helping us uncover. For centuries, scientists pondered how the universe transformed from a dark, featureless expanse into a cosmos teeming with stars, galaxies, and planets. JWST's ability to peer deep into the infrared spectrum reveals the birth of these primordial stars. These first stars, known as Population 3 stars, formed from pristine gas left over after the Big Bang, mainly hydrogen and helium, with virtually no heavier elements. Without metals, which aid cooling during star formation, these stars are believed to have been enormous, some hundreds of times the Sun's mass. Burning hot and fast, they ended their lives in supernovae. JWST glimpses galaxies just a few 100 million years after the Big Bang, providing clues about the earlier stellar populations. A key insight from JWST is that these stars were massive and short-lived. Their large size caused rapid nuclear fuel consumption, producing intense radiation, including high-energy ultraviolet light. This radiation ionized surrounding hydrogen, a process called reionization, transforming the universe from a neutral fog into a transparent cosmos. Observations suggest these stars played a vital role in ending the cosmic dark ages, lighting up the universe in a fiery glow that enabled later star and galaxy formation. Their impact extended beyond mere illumination. When these massive stars ended their lives, they exploded as supernovae, dispersing the universe's first heavy elements, carbon, oxygen, iron, into space. Since metals were virtually non-existent in the early universe, this chemical enrichment was essential for subsequent star and planet formation, and possibly life. JWST helps us understand how quickly and efficiently this enrichment occurred by witnessing the earliest dispersal of heavy elements. The influence of the first stars also set the stage for galaxy formation. Their intense radiation and supernova-driven winds carved out ionized regions, cosmic bubbles, that grew and merged, shaping large-scale structures. JWST's deep field observations reveal early galaxies, often small and irregular, composed of flickering light from these first stars. Analyzing their properties sheds light on how these stars assembled into stellar systems and how early star formation influenced their surroundings. JWST offers clues about how the first stars impacted subsequent generations. Their radiation likely cleared some gas from early galaxies, temporarily halting further star formation. In other regions, it triggered new star birth by compressing gas clouds. This feedback loop, where light and supernova both inhibit and stimulate star formation, shapes cosmic evolution, revealing a complex interplay of processes. The implications for understanding the universe's timeline are profound. Traditionally, scientists estimated first stars ignited around 300 to 400 million years after the Big Bang. JWST's observations of galaxies at redshifts over 11 push this boundary closer, capturing light from when the universe was less than a few hundred million years old. These findings provide direct evidence of when and how the first stars formed and their rapid influence on cosmic evolution. This reshapes our view of cosmic origins. Instead of a slow build-up, the universe experienced a rapid emergence of luminous objects, igniting a chain reaction that led to the galaxy-rich universe today. The first stars were not passive beacons, but catalysts for change, shaping the universe's structure, chemistry, and evolution. Their explosive deaths seeded the cosmos with heavy elements and initiated galaxy formation. Every photon captured by JWST from these early galaxies enhances our understanding of the physics governing the universe's transition from darkness into light. Decoding these signals clarifies how simple hydrogen and helium transformed into a universe filled with stars, planets, and even life. Each discovery brings us closer to answering profound questions about our origins. This ongoing exploration redefines our place in the universe. The first stars were not just distant points of light, but cosmic architects, igniting the fires that eventually led to galaxies, planets, and life itself. JWST's glimpse into the past shows that the universe's earliest light was also its most transformative, shaping everything that followed. The study of the first stars reveals their crucial role in cosmic evolution. They ended the Dark Ages, sparked chemical enrichment, and influenced galaxy formation. Their life cycles created the ingredients for subsequent stars and planets, setting the foundation for complex structures and life. JWST's observations have provided a new window into these processes, helping us piece together the story of the universe's earliest epochs. In essence, these ancient stars were part of a transformative phase that changed the universe forever. They lit the way out of darkness, dispersing metals necessary for planet formation, and initiated galaxy assembly. Their rapid formation and explosive deaths launched the universe's chemical and structural diversity, leading to the cosmos we observe today. The feedback mechanisms from the first stars, radiation and supernova, determined the pace and nature of cosmic evolution. Some regions experienced star formation shutdowns, while others saw bursts of activity. These processes continue to influence structure and complexity, as JWST's ongoing observations reveal. In conclusion, JWST's discoveries are transforming our understanding of the birth of the universe's first luminous objects. These stars sparked a cascade of events, reionization, chemical enrichment, galaxy formation, that set the stage for today's universe. Their brief, intense lives left marks on cosmic history, and ongoing studies promise to reveal more about our origins and evolution. By examining the earliest galaxies and their stellar populations, JWST provides direct insights into the processes shaping the first billion years. This knowledge enriches our understanding of cosmic history and deepens appreciation for how star formation, chemical enrichment, and feedback operate over cosmic timescales. These findings challenge and refine existing models, moving us closer to understanding our universe's dawn. Ultimately, studying the first stars helps us understand our origins. The elements that compose our bodies were forged in these stellar furnaces, intertwined with the universe's evolution. JWST's observations have unraveled new chapters of this story, revealing a universe that blossomed rapidly and profoundly after the Big Bang, giving rise to everything we see today. The James Webb Space Telescope uses its extraordinary infrared capabilities to pierce through cosmic dust and gas that often obscure the universe's most distant objects. Unlike visible light, infrared waves can travel through dense matter, allowing JWST to see into the early universe, when galaxies were just forming, and observe objects so faint that their light has travelled for billions of years. As the universe expands, the light from distant objects gets redshifted into the infrared spectrum. JWST's sensitive instruments are tuned to detect these faint, elongated signals, revealing a universe that is both ancient and vast. To identify these objects, JWST primarily relies on the near-infrared camera, the near-infrared spectrograph, and the mid-infrared instrument. The near-infrared camera captures high-resolution images of distant galaxies, stars, and possible exoplanets by taking multiple images across different infrared wavelengths. This allows scientists to distinguish objects based on their colour signatures, often revealing faint, irregular, and small structures indicative of early galaxy formation. However, capturing images is only the first step. Once potential targets are identified, JWST employs spectrographs to analyse the light in detail. The near-infrared spectrograph splits the light into wavelengths, creating spectra that serve as fingerprints for each object. These spectra reveal an object's composition, temperature, motion, and even the universe's expansion rate at the time the light was emitted. By examining specific absorption lines, scientists can identify elements like hydrogen, helium, and heavier elements, gaining insights into the chemical evolution of early galaxies. Studying these distant objects also requires confirming their distances, an essential step for understanding their place in cosmic history. JWST measures redshift, the degree to which the light's wavelength is stretched, using spectral lines like hydrogen alpha. Higher redshifts indicate objects that are farther away and older. Calculating redshift allows JWST to act as a time machine, observing the universe as it was billions of years ago. Beyond passive observation, JWST actively searches for the earliest galaxies through deep-field surveys. These involve long-duration observations focused on small patches of sky. By stacking multiple exposures, the telescope amplifies signals from the faintest objects, enabling detection of galaxies that existed when the universe was less than 1 billion years old, less than 10% of its current age. These surveys are reshaping our understanding of galaxy formation, showing some galaxies appeared very early and grew rapidly. Another technique JWST uses involves gravitational lensing. Massive galaxy clusters in front of distant galaxies act like cosmic magnifying glasses, bending and amplifying their light. This natural lensing makes it easier to detect otherwise impossible to observe objects. When combined with spectral analysis, gravitational lensing offers detailed information about the structure and composition of early galaxies, providing insights into how matter clumped together under gravity. JWST's capabilities aren't limited to galaxies. It can also study the environments of quasars, supermassive black holes actively accreting matter, and listen for signals from the first stars known as Population 3 stars. These stars are incredibly elusive due to their transient nature and distance, but JWST's infrared advantage increases the chance of detecting their faint glow. Understanding these earlier stars helps explain how they seeded the universe with elements necessary for planets and life. All these techniques work together to peel back layers of cosmic history, exposing the universe's most ancient objects in unprecedented detail. Every signal collected, every spectrum analysed, contributes a piece to the puzzle of how the universe evolved from a hot, dense state following the Big Bang into the complex cosmos of galaxies, stars, and planets we observe today. With JWST gazing deep into the past, we aren't just observing the universe. We're unravelling the story of our origins, written across space and time itself. The implications of these primordial observations are staggering. When the James Webb Space Telescope peered back in time, capturing light over 13 billion years old, it changed our understanding of the universe's true size and scope. Suddenly, the cosmos felt larger, more mysterious, and infinitely more complex than anything we had previously imagined. Viewing the universe in its earliest moments, Webb offers a glimpse into an era where the first galaxies formed from dense primordial gas. These ancient light waves carry information rewriting the cosmic timeline. Before Webb, the universe seemed a modest playground with a predictable structure evolving over billions of years. Now, it's clear that its youth was chaotic, rapid, and profoundly transformative, igniting the vast cosmic web we see today. One startling discovery is galaxies that existed just hundreds of millions of years after the Big Bang. These galaxies are unexpectedly mature and packed with stars and complex structures far earlier than scientists predicted. This pushes back the timeline of galaxy formation, indicating that the universe's initial growth was faster and more vigorous than models suggested. If galaxies could develop substantial complexity so quickly, it implies the universe's true scale extends much farther back in time, thus much larger than previously thought. The structures reveal insights into the universe's overall architecture. The distribution of these ancient galaxies hints at a vast, intricate cosmic web spanning unimaginable distances. These observations challenge existing models, prompting us to reconsider whether their current understanding can fully account for an apparently staggering universe. If the first galaxies appeared rapidly and were massive, what does that say about the universe's total volume? Could it be even more immense than current estimates? Furthermore, Webb's ability to peer through cosmic dust clouds uncovers hidden populations of early stars and protogalaxies previously invisible. These discoveries show the universe's original blueprint was far more crowded and dynamic than believed. The abundance of primordial objects points to a vast primordial universe, where the seeds of cosmic complexity spread across an enormous cosmic arena. Beyond size, these observations have profound implications for understanding the universe's fundamental nature. They raise questions about the limits of the observable universe, the roles of dark matter and dark energy, and the influence of cosmic inflation in stretching space to unfathomable proportions. Webb's data suggests what we see now is just a tiny snapshot, the tip of an endless cosmic iceberg, implying the universe stretches far beyond what any telescope has observed. The realization that early epochs were filled with rapid, intense activity urges a rethink of our cosmic origins. It hints at a universe that is vast and deeply interconnected in ways we're only beginning to understand. The primordial universe, once thought simple and small, is revealed to be sprawling, dynamic, and grand, stretching far beyond human comprehension. What does this mean for humanity? It humbles us, reminding us how tiny we are in the grand cosmic scheme, yet it fuels curiosity. The more Webb reveals, the more there is to learn. The universe's true scale reminds us how much remains hidden and waiting to be uncovered. It's a testament to our relentless quest for knowledge, and a humbling confirmation that the cosmos exceeds even our most ambitious dreams, grander and more terrifying than we ever imagined. The James Webb Space Telescope is revolutionizing our view of some of the universe's most mysterious and enigmatic objects: black holes. For decades, black holes have remained elusive, hidden behind shrouds of gas and dust, their intense gravity warping space-time to such an extreme that nothing, not even light, can escape once it crosses the event horizon. But JWST's powerful infrared instruments are now shedding light on how these cosmic giants form and evolve, providing insights that were once unimaginable. One of the key ways JWST contributes to our understanding of black holes is by observing the galaxies where they reside. Many supermassive black holes, those millions to billions of times the mass of our Sun, are nestled in the cores of galaxies, acting as gravitational anchors that influence galaxy formation and evolution. Yet, how these behemoths grow so colossal so quickly in the early universe remains a profound mystery. JWST's ability to peer back billions of years into the universe's history allows scientists to observe galaxies in their infancy, many of which already harbour active black holes known as quasars. These quasars shine brilliantly as matter spirals into the black hole, heating up and emitting intense radiation. By analysing the light from these distant quasars, JWST helps astronomers understand the processes that lead to black hole growth. Are they formed from the collapse of massive gas clouds? Do they result from the merger of smaller black holes, or perhaps a combination of both? The detailed spectral data captured by JWST can reveal the composition, structure, and activity of these early black holes, providing clues about their origins. For example, observing the surrounding gas and ultraviolet emission helps determine how quickly matter is falling into the black hole, and how these objects influence their host galaxies. Furthermore, JWST is key to studying the environment around black holes. Its infrared imaging allows scientists to see through regions of thick cosmic dust that obscure many black hole regions in visible light. This capability opens a window into the mechanisms of accretion, the process by which black holes gather matter, and the feedback effects they have on their surroundings. Black holes aren't just passive consumers of matter. Their growth often triggers powerful jets and winds that can blow through their host galaxies, regulating star formation and shaping the galaxy's evolution. JWST's ability to characterize these interactions helps piece together the dynamic relationship between black holes and their cosmic neighborhoods. But JWST isn't just observing black holes in distant galaxies, it's also helping scientists understand how stellar mass black holes, formed from the death throes of massive stars, come into existence. During a supernova explosion, a star's core collapses under gravity, potentially leaving behind a black hole. JWST's sensitivity to infrared light enables the detection of supernova remnants and the birthplaces of black holes in our own galaxy and nearby ones. By studying these stellar explosions and their aftermaths, researchers can better comprehend the conditions that lead to black hole formation. An exciting frontier lies in JWST's potential to observe intermediate mass black holes, those that are between 100 and 100,000 times the mass of the Sun, a kind of missing link in our understanding of black hole evolution. These intermediate black holes might serve as seeds for supermassive black holes. Detecting and studying them in detail could reveal the pathways through which the giants of the universe come into being. Overall, JWST is transforming our grasp of black hole physics by providing a clearer, more detailed picture of their birth, growth, and influence across cosmic history. Its infrared eyes cut through the cosmic fog, revealing the intimate relationship between black holes and the galaxies they inhabit. Every new observation helps answer some of the most profound questions. How do black holes form in the first place? How rapidly do they grow? And how much impact do they have on shaping the universe we see today? It's as if JWST is unveiling a hidden narrative, one that shows black holes as both mysterious endpoints of stellar evolution and as powerful architects of the cosmos, forever changing our understanding of the universe's most terrifying and fascinating phenomena. The James Webb Space Telescope, JWST, is transforming our understanding of dark matter, one of the universe's most mysterious components. Though dark matter can't be observed directly, its gravitational effects on visible matter, radiation, and large-scale structures reveal its presence. JWST's advanced instruments provide unprecedented insights into how dark matter influences galaxy formation and evolution, offering a fascinating picture. One primary way JWST helps understand dark matter is by studying galaxy distribution and behavior in the early universe. Galaxies tend to cluster along invisible filaments called dark matter halos, massive structures predominantly made of dark matter. These halos act as gravitational wells, pulling in gas, dust, and material needed for star formation. By observing galaxies at different distances, representing different cosmic eras, JWST maps the growth of these halos and their role in shaping large-scale structures seen today. A key advantage of JWST is its infrared capability, enabling it to peer through dense clouds of gas and dust that have historically hindered observations of distant regions. This allows astronomers to study the earliest galaxy formation epochs with greater clarity. Researchers are discovering galaxies forming within early dark matter halos, massive clumps of dark matter weighing millions to trillions of solar masses. These findings support the idea that dark matter acts as a cosmic blueprint guiding galaxy assembly through gravity. JWST not only confirms existing models, but also challenges and refines them. It has observed early universe galaxies that seem more massive and mature than some theories predicted for their ages. Such discoveries suggest dark matter halos may have prompted rapid galaxy growth earlier than expected. This raises questions about dark matter's nature. Could it interact with ordinary matter in ways that accelerate galaxy formation? Or do current models of dark matter distribution need revision? These findings prompt scientists to reconsider how dark matter behaves over cosmic time. Gravitational lensing, another critical area of study, benefits from JWST's sharp infrared vision, which enhances detection of light bending around dark matter halos. These effects allow detailed mapping of dark matter's distribution around early galaxies and galaxy clusters, providing clues about the clumping and interaction of dark matter on large scales. This reveals the unseen scaffolding influencing galaxy formation and large-scale cosmic structure. JWST also sheds light on internal galaxy dynamics through rotation curves, measurements of how fast stars and gas rotate around galactic centers. Its observations reinforce the idea that dark matter's gravitational influence extends beyond visible galaxy parts, shaping their overall structure. By comparing rotation curves across different epochs, scientists gain insights into dark matter halos' evolution and their role in matter gathering during galaxy assembly. Additionally, JWST's discoveries of faint, distant galaxies inform our understanding of dark matter's role from the universe's dawn. The distribution and abundance of early galaxies act as a cosmic census, testing dark matter models shortly after the Big Bang. Researchers analyze whether these structures align with cold, dark matter theories or suggest alternatives like warm or fuzzy dark matter. These nuanced questions are crucial for uncovering dark matter's true nature, a substance unseen, yet exerting powerful gravity. Ultimately, JWST shows that dark matter is more than a passive background. It is an active architect shaping the universe. Its gravity influences galaxy formation, growth, and distribution across cosmic history. It drives galaxy clustering, helps form large-scale structures, and impacts internal galaxy makeup. Studying galaxy formation within dark matter's influence brings us closer to understanding the universe's fundamental fabric, its invisible skeleton underpinning all observable matter. Each new observation adds complexity to this cosmic puzzle, bringing us closer to answers about one of the universe's deepest mysteries. Throughout these investigations, JWST is transforming dark matter from an elusive theory into a dynamic, central player in cosmic evolution. Its detailed observations of galaxy formation, distribution, and internal dynamics are reshaping theories and challenging assumptions about dark matter's properties. Its role as a cosmic scaffolder underscores the interconnectedness of matter on large scales and highlights dark matter's importance in shaping cosmic history. As JWST continues its mission, it promises to deepen our understanding of dark matter's influence on galaxy formation and large-scale structure. From early universe research to detailed galaxy dynamics, it offers vital clues about the unseen mass holding the universe together. The more we learn, the clearer it becomes that dark matter is not just a background component but a fundamental force shaping cosmic evolution. Its gravitational influence acts as an invisible blueprint, dictating the formation and arrangement of galaxies and clusters across time. With JWST's observations, we gain a deeper appreciation of this unseen architect, bringing us closer to unraveling one of the universe's most profound mysteries. Exactly 660 words. The James Webb Space Telescope, JWST, isn't just peering back in time to see the first galaxies or star birthplaces. It's revolutionizing our understanding of one of the universe's greatest mysteries, dark energy. This elusive force makes up about 70% of the universe's total energy, yet its true nature remains one of the most profound enigmas in science. Thanks to JWST's sensitivity and infrared capabilities, scientists are gaining new insights into cosmic expansion and how dark energy influences it. Understanding dark energy hinges on measuring how the universe grows over time. For centuries, astronomers observed that galaxies seem to be moving away from each other, with more distant galaxies receding faster, a phenomenon called cosmic expansion, first discovered by Edwin Hubble. The key question is whether this expansion is speeding up or slowing down. Decades of observations support that it's accelerating, driven by dark energy's mysterious repulsive effect. Here, JWST's ability to probe deep into the universe becomes vital. Its infrared instruments can look through cosmic dust clouds and detect faint light from galaxies that formed billions of years ago. This enables scientists to observe different epochs of the universe's history, creating a timeline of its growth. By comparing the distances to galaxies with their velocities, their recessional speeds, researchers can trace how the expansion rate, known as the Hubble constant, has evolved over cosmic time. Previously, measurements of the Hubble constant from different methods, such as supernovae or the cosmic microwave background, have shown slight discrepancies. JWST's capacity to observe galaxies at intermediate distances helps bridge this gap, providing more precise, consistent data. Analyzing the brightness and redshift of distant supernovae and galaxy clusters allows for refined measurements of the universe's expansion at various points in time. These findings help infer the influence of dark energy on cosmic acceleration. But JWST isn't just refining existing data. It is opening new avenues of exploration by examining the universe's large-scale structure. Galaxies aren't randomly distributed, but form a cosmic web of clusters, filaments, and voids. JWST's detailed mapping of these structures offers clues about how dark energy affects their formation and evolution. If dark energy remains constant, as Einstein's cosmological constant suggests, the growth of the cosmic web should follow predictable patterns. Any deviations could point to a more complex dynamic form of dark energy. Moreover, JWST can investigate the dark energy equation of state, which describes how dark energy's density changes as the universe expands. Observing distant supernovae and galaxies enables scientists to test whether dark energy is constant or evolving. Such data could reveal a varying dark energy density, hinting at new physics beyond Einstein's general relativity, and possibly leading to breakthroughs in our understanding of the universe's fundamental fabric. JWST's data also enhances comprehension of cosmic voids, vast, nearly empty regions of space that expand faster than denser areas. These voids serve as natural laboratories to study dark energy's influence on cosmic expansion. As JWST maps these regions with high precision, researchers can better understand how dark energy impacts different environments, further illuminating the forces driving acceleration. The implications of uncovering dark energy's true nature are staggering. It could reshape physics. Is dark energy a constant cosmological term, or a dynamic field that changes over time? JWST's observations are crucial for narrowing down these possibilities, shaping future theories, and understanding the universe's underlying laws. In essence, JWST functions as a cosmic detective, meticulously collecting evidence about the universe's expansion from its fiery beginnings to its vast current state. Its insights into dark energy shed light on the reason behind cosmic acceleration and what this might mean for the universe's ultimate fate. With each observation, scientists move closer to understanding the force that propels cosmic expansion at an ever-increasing speed. The quest could ultimately reveal whether dark energy is a permanent feature or indicates deeper, more profound principles governing the universe itself. Recent discoveries by the James Webb Space Telescope have truly shattered previous boundaries of our understanding, revealing secrets of the universe that are both awe-inspiring and, in some cases, downright terrifying. It's as if the universe has just handed us a list of its deepest, darkest mysteries, ones that challenge everything we thought we knew. One of the most astonishing revelations has been the discovery of galaxies that formed just a few 100 million years after the Big Bang. These stellar cities, often containing billions of stars, appeared to be much more developed than scientists had predicted for such an early epoch. It's as if the universe, in its infancy, had already gotten a head start, rapidly forging massive galaxies in a cosmic sprint that defies our current models of galactic evolution. The implications are staggering. Maybe the universe's timeline of formation is more complex and faster than previously thought, or perhaps there are unknown processes that accelerated galaxy growth. Moreover, the JWST has directly observed the earliest known star-forming regions, capturing light from the very first generation stars, known as Population 3 stars. These stars, formed from pristine hydrogen and helium, are believed to be the first sparks of light after the universe's dark ages. Yet they've remained elusive for decades, shrouded in cosmic mystery. Now, with JWST's incredible infrared sensitivity, astronomers have glimpsed the faint glow of these primal stars, giving insight into how the universe's first light ignited. This discovery has profound implications for our understanding of how matter clumped together under gravity, igniting the process that would lead to planets, life, and everything in between. But perhaps even more unsettling has been the telescope's observation of distant, supermassive black holes, some less than 1 billion years after the Big Bang. These black holes, with masses 1 billion times that of our Sun, challenge existing theories about how black holes grow so rapidly. How could these be so massive in such a short span? It's a cosmic mystery that hints at unknown mechanisms of black hole formation, or perhaps even exotic phenomena that accelerate their growth. These black holes are like cosmic predators, lurking silently in the early universe, and their existence pushes scientists to rethink the very fabric of cosmic evolution. The JWST has also uncovered peculiar, seemingly primitive galaxies with surprisingly low metallicities, meaning they contain fewer heavy elements than expected for their age. This suggests that some parts of the universe remained in a sort of primordial state longer than scientists believed, hinting at pockets of cosmic infancy persisting amidst a universe that seemed to be rapidly evolving. These galaxies act as time capsules, offering glimpses of conditions that resemble the universe's most ancient era, though their existence raises questions about the uniformity of cosmic development. On a more disturbing note, JWST has started to find evidence of early signs of cosmic reionization, the process that rendered the universe transparent to ultraviolet light by stripping electrons from atoms. While reionization marks one of the universe's most pivotal transitional periods, the amount of variation observed in different regions suggests a patchy, uneven process. This uneven reionization paints a picture of a universe that might still hold regions of darkness, where the light has yet to fully penetrate, hinting at vast, unexplored regions that remain shrouded in cosmic shadows. In the realm of exoplanets, the JWST is revolutionizing our understanding of alien worlds. Recently, scientists have detected complex organic molecules in the atmospheres of distant exoplanets, some of which are located within their stars' habitable zones. The presence of these molecules, precursors to life, raises the terrifying yet thrilling possibility that life might not be a unique phenomenon on Earth. As JWST peels back the layers of alien atmospheres, we begin to realize that the universe is teeming with environments where life could potentially thrive, shattering our notions of uniqueness and comfort. These discoveries aren't just scientific milestones, they are cosmic shocks that challenge our place in the universe. Each new observation from JWST peels back another layer of cosmic darkness, revealing a universe that is older, stranger, and far more mysterious than ever imagined. The scale of it all is both humbling and exhilarating, reminding us that we are only just beginning to decode the universe's secrets, and that the road ahead holds even more astonishing revelations waiting in the cosmic shadows. As the James Webb Space Telescope peels back cosmic layers, its revelations are staggering. Each image and spectrum pushes the boundaries of understanding, confronting us with a universe vastly more expansive and mysterious than imagined. The vastness stretches in every direction, billions of light years, making Earth seem like a tiny speck amid an infinite sea of stars and galaxies. But it's not just the scale that reveals the universe's terrifying grandeur. It's the implications behind what Webb shows us, the reality of how small, fragile, and insignificant we truly are. Webb captures distant galaxies that formed mere hundreds of millions of years after the Big Bang, offering a glimpse into an ancient universe predating human existence. These galaxies are incredibly distant, their light travelling billions of years to reach us. The fact that we can observe such faint signals from an epoch close to the universe's birth is mind-boggling. It's like reaching back in time, witnessing the universe's early chaos and aftermath, and realising it was a wild, tumultuous place at its inception. These early galaxies are enormous, often packed with stars more massive and dense than modern ones. This intensity suggests a universe that was once an unfathomably energetic environment, shaped by violent processes that remain elusive and incomprehensibly destructive. Webb also unveils star and planetary birthplaces, fascinating yet terrifying in their scale and complexity. These stellar nurseries, thick with clouds of gas and dust, glow with raw energy. They remind us how worlds like ours originate amid chaos, where gravity and nuclear fusion ignite in explosive bursts of light and matter. What's unsettling is that this vital process is just a tiny part of a universe constantly churning out billions of new stars and planetary systems on colossal scales. The number of planets, moons, and potential habitats out there is mind-blowing, raising unsettling questions about our uniqueness, or lack thereof. Beyond galaxies and star-forming regions, Webb's findings about exoplanets and atmospheres that might contain ingredients for life take fears to a darker level. As Webb analyzes atmospheric compositions, it reveals staggering diversity among planetary environments. Some worlds might be inhospitable, barren wastelands, others too extreme for life as we know it. The idea that many planets could be hostile, uninhabitable wastelands is chilling. It underscores how fragile conditions for life are and suggests the universe may teem with planets that are frozen, scorched, or poisoned by radiation, making us feel alien, insignificant in a universe where life is rare and precious. The most terrifying aspect lies in scale, an almost incomprehensible, nihilistic enormity. Every galaxy Webb observes is merely one among billions, each harbouring billions of stars, each star potentially with planets. This cosmic assembly line has been ongoing for nearly the universe's entire age. Its size defies imagination, stretching beyond mental grasp, filled with phenomena challenging our understanding. It's both awe-inspiring and terrifying to realize how tiny our cosmic footprint truly is. We are like a flickering candle in an infinite cosmic storm, overshadowed by the vastness surrounding us. This humbling realization makes it clear. We are tiny players in a vast, ancient universe that neither cares for nor recognizes our existence. Yet Webb's insights reveal that this scale, this incomprehensible magnitude, is intrinsic to reality. Exploring the universe's grand design exposes the raw truth of our vulnerability and insignificance amid an unfathomably vast cosmos unfolding for over 13 billion years, continuing long after we're gone. The universe's size and complexity challenge us to accept our place within it, fragile and fleeting, yet connected to the cosmic whole. The more we learn, the more we recognize the breathtaking scale that surrounds us, a reminder that we are merely a brief spark in an endless, awe-inspiring universe. The James Webb Space Telescope is transforming our understanding of galaxy formation and evolution. Think of the universe as a vast, dynamic tapestry. JWST acts like a fine spectroscope, helping us peel back layers of time and space to reveal the intricate threads of galaxy formation. A key aspect of JWST's mission is its ability to look back to the universe's earliest epochs, just hundreds of millions of years after the Big Bang. Before JWST, astronomers glimpsed these initial galaxies but with limited detail, their faint light often obscured by cosmic dust. JWST's infrared capabilities enable it to penetrate this dust, bringing into focus galaxies in their infancy. It uncovers how these structures formed from tiny fluctuations in dark matter density, which arose as gravitational wells drawing in gas and dust. Galaxy formation is not a smooth, steady process, but a tumultuous, often chaotic one. JWST reveals evidence of rapid star formation in young galaxies, stars igniting in bursts as gas collapses under gravity. Early galaxies are surprisingly small and irregular, frequently shaped by mergers and interactions. These cosmic collisions are akin to traffic jams, forcing galaxies to merge, grow, or splinter apart, sculpting their shapes and structures. As the universe matures, galaxies tend to become more stable, evolving into spirals or elliptical forms. JWST helps us understand that these transformations are driven by internal processes, such as supernova explosions and black hole activity, and external influences like mergers with smaller galaxies. By observing the same regions across different epochs, JWST creates a cosmic documentary, illustrating the pathways from nascent galaxies to their mature counterparts. An emerging insight from JWST is the importance of environment in galaxy evolution. Galaxies are not isolated but part of larger structures. Dense clusters influence each other through gravity, gas exchange, and the merging of supermassive black holes. JWST's ability to capture light from various distances reveals how galaxies in crowded regions evolve differently from isolated ones. This hints that the universe's web-like large-scale structure, its filaments and voids, guides galaxy formation. Another key finding relates to feedback mechanisms. Energetic events like supernovae or jets from supermassive black holes can regulate star formation. They can eject gas or heat it, preventing rapid star formation. JWST's detailed observations of these processes shed light on why some galaxies sustain star creation over billions of years, while others age quietly with depleted or expelled gas. JWST also enhances our understanding of dark matter's role. While invisible, dark matter provides the gravitational framework for galaxy assembly. By studying star and gas motions within galaxies, JWST helps map the distribution and growth of dark matter halos. This deepens our knowledge of how unseen matter influences the visible universe's structure over billions of years. Every galaxy imaged by JWST challenges prior assumptions and prompts us to revise theories. Some observations suggest galaxies experienced intense, rapid starburst phases much earlier than expected, hinting at a universe more active in its youth. Others reveal supermassive black holes formed surprisingly quickly, sometimes before their host galaxies were fully assembled. These surprises make us refine models of cosmic evolution. Essentially, JWST acts as a cosmic time machine. More than just a distant galaxy viewer, it's a tool for understanding the processes that shape the universe. It shows galaxy formation involves chaos and order, violent collisions and gentle accretion, driven by dark matter and fueled by gas and dust. Galaxies are not static monuments, but living entities, evolving over billions of years and across vast distances. With every discovery, JWST pushes the boundaries of our knowledge, revealing how the universe's grand structures come into being and change. It reminds us the cosmos is a continuously evolving, awe-inspiring spectacle, full of surprises, mysteries, and beauty. As we explore, we strive to understand our universe's deepest secrets. The James Webb Space Telescope has transformed our understanding of star formation across cosmic history. Before JWST, astronomers glimpsed star formation in nearby or distant galaxies with limited detail. Now, with unprecedented sensitivity and resolution, JWST reveals a dynamic story of where, when, and how stars formed over billions of years. One of the most surprising findings is how prolific star formation was in the early universe during the first few billion years after the Big Bang. Galaxies during this era, called the Cosmic Dawn, blazed with new stars when the universe was a fraction of its current age. Data shows star formation rates soared during this period, sometimes reaching hundreds or thousands of times higher than today. This intense stellar birth wasn't limited to small galaxies. Some massive early galaxies formed stars rapidly, challenging previous models suggesting slow growth. JWST's ability to peer into the infrared was crucial because the earlier star-forming regions are shrouded in cosmic dust that absorbs visible light. These dust clouds glow brightly in infrared, guiding scientists directly to sites of intense star formation previously hidden. Consequently, JWST reveals that the universe's most vigorous star-forming periods occurred much earlier and faster than previously thought. The findings suggest the universe's stellar factory was in overdrive shortly after the first galaxies formed, producing a cosmic fireworks display that laid the groundwork for today's complex structures. However, star formation didn't stay at such high levels forever. Data indicates that rates declined significantly after peaking around 10 billion years ago. This decline hasn't been uniform. JWST uncovers a mosaic within galaxies where star formation waxes and wanes, driven by local conditions and cosmic events. Some galaxies undergo short, intense bursts of star formation, while others remain relatively quiet. This variation points to complex feedback processes, supernova explosions, black hole activity, gas inflows and outflows that regulate star formation. The decline in star formation seems connected to the universe's expansion and the depletion of gas, the raw material for stars. As galaxies exhaust their gas supplies and conditions become less favourable, overall rates decline. Still, JWST uncovers pockets of renewed activity, suggesting star formation can ignite under the right circumstances even as the universe grows older and more diffuse. JWST also reveals a remarkable diversity in star-forming regions across cosmic time. In some early galaxies, stars formed chaotically, weaving gas and dust into complex networks. In more mature galaxies, star formation adopts a steadier, quieter rhythm. Today, JWST identifies young star clusters emerging from dusty cocoons, emphasizing that stellar birth is ongoing and universal. These findings challenge earlier models predicting a steady star formation history. Instead, JWST shows a universe characterized by bursts of rapid creation, followed by quieter epochs. This energetic, unpredictable cosmos defies simple explanations. The universe's fabric, space, energy, gravity, drives a complex dance, fostering periods of intense activity and calm. Every observation deepens our wonder and raises questions about the universe's fragility and youth. Each breakthrough underscores how fleeting the conditions for life and the universe itself might be. The story of star formation narrates ongoing creation, transformation, chaos, and order through cosmic time. It continues to unfold in astonishing and sometimes unsettling ways. JWST isn't just revealing stars, it's illuminating our place within an immense, ancient universe that's constantly changing. The interplay of past, present, and future is woven into an intricate cosmic tapestry far beyond human understanding. These insights deepen our knowledge of the universe's complex evolution, showing how dynamic and unpredictable the cosmic landscape is. They also remind us how much remains to be discovered, as each new revealed raises further questions about galaxies, stars, and life's origins. The telescope's findings about star formation are reshaping views of cosmic history. They depict a universe marked by extraordinary bursts of activity, followed by quieter periods, an uneven, energetic landscape. This challenges ideas of a steady, predictable universe and suggests that cosmic evolution involves chaos and order intertwined. Understanding star formation through JWST enhances appreciation of the universe's complexity and resilience. Star nurseries are remarkably adaptable, functioning under varying conditions across epochs. From chaotic regions in ancient galaxies to calmer, more mature systems, star formation persists, testament to its fundamental role in cosmic evolution. Ultimately, JWST's discoveries reveal that the universe's history is a story of growth, destruction, renewal, and chaos, an ongoing saga spanning billions of years. Past, present, and future are deeply interconnected within a vast, intricate fabric that continues to surprise us. The story of star formation remains incomplete. Each observation offers a new chapter toward understanding our cosmic origins. In sum, JWST depicts a universe with a tumultuous, vibrant past and an evolving present filled with diverse regions and processes. It highlights a cosmos of bursts of creation, complex feedback mechanisms, and pockets of renewed activity amid overall decline. These insights reshape our view of cosmic history, emphasizing star formation as a dynamic, ongoing saga unfolding in unexpected ways. Have you ever wondered how the vast patterns of stars, galaxies, and emptiness came to be arranged as they are? The universe isn't just a collection of isolated stars. It features an intricate web of cosmic filaments and enormous structures called the large-scale structure of the universe. These structures act as the universe's skeleton, shaping its overall form. How do these massive filaments and structures form and evolve? To understand their origins, we must look back to just after the Big Bang. Initially, the universe was nearly uniform, hot, dense, filled with particles and radiation. Tiny quantum fluctuations existed in this early state, small variations in density, signatures of quantum uncertainty frozen into space-time. As the universe expanded and cooled, these tiny differences became the seeds for future structures. Gravity, the driving force of cosmic evolution, began to amplify these density differences. Over billions of years, regions slightly denser than their surroundings pulled in more matter. This process's gravitational instability. Denser areas became even denser, forming the first stars, galaxies, and clusters, while less dense regions grew emptier, creating vast voids. These gravitational processes didn't produce isolated galaxies, but rather directed matter along filamentary structures, web-like strands. Imagine a three-dimensional spiderweb stretching across space, with galaxies at the intersections called nodes. These nodes often host massive galaxy clusters, some containing hundreds or thousands of galaxies. The filaments themselves serve as cosmic highways, channeling gas, dark matter, and galaxies toward these dense clusters. The formation of these large-scale features is complex. Initial tiny fluctuations in density didn't just randomly cluster matter, they directed the emergence of a networked pattern. Dark matter, which comprises about 85% of all matter, plays a crucial role here. Though invisible, dark matter's gravitational pull provides the scaffolding upon which visible matter, stars, gas, and galaxies assemble. Without dark matter, the formation of large structures would be much less efficient. As the universe aged, these filaments and clusters became more pronounced. Gas falling along the filaments heated up as it collided and compressed, igniting star formation in galaxies. The densest nodes, intersections of multiple filaments, became galaxy clusters, densely packed regions of hundreds or thousands of galaxies. These dense regions experience interactions, collisions, and mergers, which grow supermassive black holes and trigger bursts of star formation, or galactic winds. The evolution of these large-scale structures depends on cosmic expansion. In the universe's early history, gravity dominated, pulling matter inward and intensifying the cosmic web. But as dark energy, a mysterious force driving accelerated expansion, began to dominate, it stretched space-time and slowed the growth of structure. Now, in the universe's mature phase, this acceleration has effectively frozen the large-scale patterns, preserving the web as a frozen masterpiece, reflecting the universe's dynamic history. Cosmic filaments and structures continue evolving. Galaxies move along filaments, merging and interacting, fueling star and black hole growth. Some filaments may stretch and thin, others thicken with matter influx. Over long timescales, gravity ensures increasing complexity, interconnectedness, and massiveness of these structures. Yet, on the grander scales, the universe's expansion tends to stretch everything apart, spreading structures farther apart. The James Webb Space Telescope helps us understand this cosmic web's history. Observing distant galaxies and their arrangements billions of years ago reveals how structures emerged from initial fluctuations. JWST allows us to see how filaments formed, how matter accumulated at nodes, and how the universe's expansion shaped these structures. Essentially, the story of cosmic filaments and large-scale structures is of the universe's early quantum fluctuations transforming into the vast web that holds everything together. It is a testament to gravity's relentless power and dark matter's invisible influence, an ongoing dance across space and time, spun out of the chaos after the Big Bang. As we explore these cosmic threads, we realize we are part of this vast tapestry, woven into a universe as mesmerizing as it is grand. Dark matter and dark energy are fundamental, yet mysterious components that profoundly influence the universe's structure, evolution, and ultimate fate. Together, they account for roughly 95% of the cosmos. Dark matter makes up about 27%, while dark energy accounts for approximately 68%. Their effects are invisible to us but are inferred through gravitational and dynamical impacts, shaping the universe in complex and astonishing ways. Dark matter acts as an invisible scaffolding that holds galaxies and galaxy clusters together. Unlike ordinary matter, which interacts with light and can be observed through telescopes, dark matter does not emit, absorb, or reflect electromagnetic radiation. Its presence is inferred from evidence like galaxy rotation speeds, which suggest more mass than visible matter accounts for. Gravitational lensing, the bending of light from distant objects, also indicates unseen mass within galaxy clusters. Dark matter thus constitutes about 85% of all matter in the universe, and plays a key role in forming the large-scale cosmic web. Dark matter's primary role is to serve as gravitational glue, providing the mass necessary for galaxies and large structures to form and stay stable over cosmic timescales. In the early universe, tiny quantum fluctuations created slight density variations. Because dark matter interacts weakly with radiation and particles, it began clumping early, forming vast halos of dark matter. These halos were gravitational wells that attracted baryonic, ordinary matter, which then cooled and condensed into stars and galaxies. Without dark matter, the universe's structure would be vastly different. Galaxies would lack the necessary mass to sustain observed rotation curves, resulting in a much more diffuse, disorganized universe. Dark matter not only influenced initial structure formation, but also affected their subsequent evolution. It acts as the backbone upon which galaxy clusters and superclusters are built, guiding matter into filaments connecting cosmic voids. Simulations confirm that dark matter's gravity is essential for producing the filamentary universe observed today. It enables galaxies to form at the centers of dark matter halos, where conditions are dense enough for star formation. The distribution and clustering of dark matter are thus vital to understanding galaxy morphology, size, and distribution over cosmic time. On larger scales, dark energy plays a contrasting yet equally critical role. It is an enigmatic form of energy that permeates space itself, driving the universe's accelerated expansion. Unlike dark matter, which pulls matter inward through gravity, dark energy exerts a repulsive effect, stretching space-time at an increasing rate. Observations of distant supernova, cosmic microwave background radiation, and large-scale structures confirm that the universe's expansion has been speeding up for several billion years. Visualize dark energy as an invisible force that pushes the fabric of space outward, overcoming gravity. As the universe expands, dark energy's influence grows because its density remains nearly constant, unlike matter, which becomes more diluted as space increases. This accelerated expansion has profound implications. In the distant future, galaxies outside our local group will recede beyond our observable horizon, making the universe appear emptier and more isolated. If dark energy continues to dominate, the universe could evolve into a cold, dark, lonely place, an endless, exponentially expanding void. The interaction between dark matter and dark energy resembles a cosmic tug of war. Dark matter pulls matter inward, fostering galaxy and cluster formation, while dark energy drives everything apart, causing accelerated expansion. This balance determines the universe's shape, size, and long-term evolution. Too much dark energy could cause rapid expansion, preventing large structures from forming. Too little might lead to a recollapse, or big crunch. Current observations suggest the universe is finely balanced, with accelerating expansion and enough structure to host galaxies and life. In essence, dark matter and dark energy are the unseen architects of the cosmos. They control the distribution of matter, the formation and evolution of structures, and the universe's ultimate destiny. Though their true natures remain elusive, scientists are actively exploring them through advanced telescopes, particle experiments, and theoretical models. As insights grow, it becomes clear that much of space operates under unseen influences, forces holding the universe together and pushing it outward, driven by matter and energy beyond our direct perception. Their mysteries challenge our understanding of physics and suggest a deeper, more fundamental layer of reality, possibly involving new particles, laws, or dimensions. The universe's vast scale and complexity result from these hidden forces, which have shaped it from its inception and continue to steer its future in the endless expanse. The revelations brought forth by the James Webb Space Telescope serve as a cosmic mirror, forcing us to confront how tiny and fragile our existence truly is within the grand tapestry of the universe. When we peer back into space and time, glimpsing galaxies formed billions of years ago, we're not just witnessing starbirth or celestial evolution. It's a stark reminder that our civilization exists within a fleeting moment in the cosmic timeline. The universe's vastness is no longer just a figure of speech. It becomes an overwhelming reality, a scale so immense it defies human comprehension. One of JWST's most haunting revelations is the ancient galaxies scattered across the cosmos. Formed mere hundreds of millions of years after the Big Bang, these galaxies challenge our understanding of cosmic timelines. They show us that the universe was once a chaotic, energized place, expanding rapidly and evolving faster than we imagined. Each piece of this cosmic puzzle reveals an uncomfortable truth. Earth and humanity are tiny blips in an ageless universe that predates our ancestors' gaze upon the stars. The scale stretches beyond imagining. Billions upon billions of galaxies, each containing billions of stars. In this infinity, our sun is a faint spark of light, dwarfed by galaxies spanning hundreds of thousands of light years. As JWST uncovers more about star formation and planetary systems, we realize how fleeting and precarious our existence is. Stars are born, burn brightly, and die, all within cosmic blink-of-an-eye timescales, reminding us that the universe's scale is not only enormous, but also indifferent to life. While Earth's origins are a miraculous spark amid chaos, stellar processes also create hostile environments. Planets form lush and capable of life, but they remain vulnerable, subject to cosmic collisions, supernova, and gamma-ray bursts that threaten their existence on timescales insignificant compared to cosmic ages. Dark matter and black holes deepen this sense of cosmic terror. Black holes can devour entire stars, revealing how much remains hidden in the universe's shadows. Dark matter's mysterious influence shapes galaxy formation, yet most of the universe's mass is invisible, comprising about 90% of all matter, indifferent to human curiosity. These phenomena remind us how unseen forces exert enormous influence, bending reality and stretching the limits of our understanding. Dark energy, causing the universe's expansion to accelerate, pushes this scale into a nearly unfathomable realm. The universe isn't just immense, it's actively tearing itself apart, with galaxies receding faster than light, an ongoing, terrifying cosmic breakup. This relentless expansion hints at an ultimate fate, a universe stretched into silence or swallowed by the unknown, where what we know may unravel before our eyes, leaving us to question whether anything endures long enough to hold meaning. All these insights serve as a sobering reminder that the universe, in its vastness and complexity, is fundamentally indifferent and terrifying. We are fortunate to exist on this tiny blue planet, amid a universe so colossal that distances and timescales challenge human intuition. Every new JWST discovery pushes this perspective further, forcing us to face the reality that human life, civilizations, and even our understanding are ephemeral whispers in the roaring silence of space. It's humbling, breathtaking even, how mighty and mysterious our cosmic home is. This universe is so vast that we are left both in awe and overwhelmed by our insignificance within it. The James Webb Space Telescope, JWST, is a groundbreaking tool in the search and study of exoplanets, planets beyond our solar system. Its extraordinary sensitivity and advanced instruments have revolutionized our ability to understand these distant worlds, revealing their atmospheres, climates, and signs of potential habitability. JWST's contributions extend beyond mere detection. It unlocks their secrets, helping us comprehend what these planets are truly like. One of JWST's main methods for studying exoplanets is transit spectroscopy. When a planet passes in front of its star, a tiny amount of starlight filters through the planet's atmosphere. Analyzing this light at various wavelengths allows JWST to detect chemical signatures, molecular fingerprints, that reveal atmospheric composition. Detecting gases like water vapor, carbon dioxide, methane, or complex organics offers clues about a planet's environment and potential habitability. During transits, JWST's near-infrared spectrograph, NIR-SPEC, and mid-infrared instrument MIRI capture detailed spectra, creating atmospheric profiles that were previously impossible to obtain. These spectra help determine if a planet has cloudy or clear atmospheres, thick or thin layers, or greenhouse gases affecting surface conditions. Such data are crucial for assessing whether a planet could support liquid water or sustain life processes. Beyond transit spectroscopy, JWST's capacity for direct imaging marks a notable breakthrough. While challenging, it can directly observe some young, massive exoplanets orbiting far from their stars. These planets still emit heat from formation, making them visible against the bright star background. Using instruments like coronagraphs to block starlight, JWST can capture images of these worlds, enabling atmospheric studies. Observing weather patterns, cloud cover, and seasonal variations provides insights into their climate and atmospheric dynamics. A key focus is the search for Earth-like planets within the habitable zones of nearby stars. Direct detection remains difficult, but JWST's ability to analyze their atmospheres is vital. Studying known exoplanets in habitable zones, scientists look for biosignature gases, oxygen, methane, or other molecules associated with biological activity. Finding such gases in the right ratios could suggest ongoing biological processes hinting at life. JWST advances understanding of planetary formation and evolution by analyzing atmospheres across a range of exoplanets, from scorching hot Jupiters to icy super-Earths, to reveal how planetary systems develop. Researchers investigate whether planets gain or lose specific gases over time, or how atmospheres change due to stellar interactions. These insights inform broader theories of planetary system formation, illustrating how diverse worlds arise and evolve. Furthermore, JWST is instrumental in studying planets orbiting stars of various types and ages. Faint stars like red dwarfs, abundant and often hosting potentially habitable planets, pose observational challenges for earlier telescopes. JWST's capacity to probe these stars' atmospheres helps determine if their planets could support life despite stellar activity. This broadens our knowledge of habitability under different stellar environments. As it explores this diversity, JWST transforms our understanding of planetary variety. It uncovers planets with exotic atmospheres, unusual chemistry, and climates unlike those in our solar system. Such discoveries inform estimates of how common habitable worlds might be, shaping our comprehension of potential life-supporting planets and the universe's capacity to host life. The telescope's impact extends beyond individual findings. It refines models of planetary atmospheres and climates, which are essential for guiding future missions focused on biosignatures and habitability. The data contribute to the broader effort to determine whether Earth is unique or if worlds similar to ours are common, providing context for humanity's place in the cosmos. In the quest to understand our universe, JWST offers vital pieces, detailed portraits of distant planets, once only faint points of light. Its observations help answer age-old questions. Are we alone? What are these worlds like? How do they fit into the universe's story of birth, growth, and diversity? By unveiling atmospheres, climates, and potential signs of life, JWST expands our knowledge and fuels curiosity about the cosmos. Its discoveries bring us closer to understanding how widespread life might be and how unique Earth truly is. As JWST continues its exploration, its contributions will shape astrophysics and planetary science for decades, providing insights into worlds beyond our solar system. The James Webb Space Telescope's groundbreaking observations mark a new chapter in understanding worlds beyond our solar system. One of its most significant contributions is the detailed characterization of exoplanet atmospheres, layers of gases enveloping planets orbiting distant stars. With JWST's advanced instruments, scientists are now uncovering the complex compositions that reveal these worlds' histories, climates, and potential for life. Before JWST, astronomers mainly detected exoplanets indirectly, observing star dimming during transits or gravitational effects. Now, JWST's ability to analyze starlight passing through exoplanet atmospheres has been transformative. During a transit, some light filters through the planet's gaseous envelope, and JWST's spectrometers identify the specific wavelengths molecules absorb, revealing components like water vapor, carbon dioxide, methane, and exotic molecules. Detecting water vapor is particularly exciting. While its presence doesn't guarantee habitability, it indicates the potential for liquid water, a fundamental ingredient for life. Water vapor has been observed in atmospheres of planets orbiting various star types, including sun-like stars and red dwarfs. These findings suggest water-rich worlds are common, even in star systems different from our own, broadening the scope of habitable environments. In addition to water, JWST has analysed atmospheres with high levels of greenhouse gases, such as carbon dioxide, providing insights into climate dynamics. These gases influence planetary temperatures and climate stability. Thick, CO2-rich atmospheres could trap heat, leading to extreme conditions, while balanced atmospheres might support habitable environments. The presence of hazes and clouds, detectable by JWST, adds complexity, signalling weather systems and atmospheric chemistry. Some exoplanets exhibit hazy layers akin to Earth's smog but composed of different materials, shaped by unique atmospheric processes. The diversity of planetary atmospheres revealed highlights a universe teeming with different worlds. Some exoplanets have dense, Venus-like atmospheres, with crushing pressures and uninhabitable conditions. Others possess thin, tenuous atmospheres where gases escape into space, hinting at primordial or evolving states. Yet, the detection of water vapor and other molecules supporting life raises the possibility that some planets could host life, or microbial life forms. Scientists are now refining models of exoplanet habitability using JWST data. Factors like atmospheric composition, radiation, and surface conditions are being studied to identify promising targets. The detection of stable water vapor in temperate atmospheres suggests that, under right conditions, liquid water could exist on the surface, fulfilling a key criterion for life. Although still early, these insights help narrow down worlds worthy of closer examination. Furthermore, JWST challenges previous assumptions about planetary atmospheres being static and uniform. Instead, many are dynamic, chemically rich, resembling miniature versions of Earth's atmosphere, yet vastly different in composition and context. This complexity provides clues about planetary evolution, how atmospheres form, change, and sometimes disperse over millions of years. Understanding these processes allows scientists to better grasp how planets develop habitability potential over time. The implications extend beyond finding habitable worlds. They reveal how atmospheres are shaped by host star radiation, magnetic fields, and geological activity. These interactions can strip atmospheres away or replenish them, influencing whether a planet remains a cradle for life or becomes barren. JWST offers the first glimpses into these processes on worlds many light years away, deepening our understanding of planetary environments. While these discoveries are awe-inspiring, they also humble us. The universe's vastness and intricate atmospheric chemistry remind us how little we currently understand about distant worlds. The search for life is not just about finding habitability, but understanding the universe's potential. Each new atmospheric spectrum brings us closer to answering the profound question: are we alone? As JWST continues to scan distant planets, our picture of the universe grows richer and more complex. Each molecule identified and signature detected adds to the cosmic mosaic, a reminder of a universe that is immense, ancient, and full of possibilities. These findings could someday lead us to discover other forms of life among the stars, transforming our understanding of our place in the cosmos. The ongoing exploration of exoplanet atmospheres promises to reshape our understanding of planetary evolution, climate, and habitability. With each observation, we learn about the diversity of worlds beyond Earth and the factors necessary for life. This knowledge not only informs future missions, but also fuels our curiosity about the universe's potential, an ever-expanding quest to discover whether we are truly alone or part of a vast interconnected cosmic web. The James Webb Space Telescope, JWST, greatly advances the search for Earth-like planets around distant stars, thanks to its exceptional sensitivity and sophisticated instruments. Its infrared observation capability allows it to detect faint signals that other telescopes might miss, opening new avenues for identifying planets in the habitable zone, where conditions could support liquid water. One primary method JWST uses to find habitable zone planets is transit spectroscopy. When a planet crosses in front of its star, it causes a slight dip in brightness. JWST's precise instruments can detect these tiny changes. Observing multiple transits enables detailed atmospheric analysis. During a transit, starlight filters through the planet's atmosphere, with molecules like water vapor, carbon dioxide, methane, or oxygen, absorbing specific wavelengths and creating characteristic absorption fingerprints. Analyzing these fingerprints allows scientists to determine atmospheric composition with high accuracy. Detecting a planet is not enough. Understanding its environment and potential habitability is crucial. Infrared observations are especially important because they can identify molecules vital for life or indicators of biological activity. Water vapor, which absorbs infrared strongly, suggests the presence of water on or within the planet's surface or atmosphere. Detecting gases such as methane or oxygen, especially if they are in disequilibrium, could hint at biological processes, since their atmospheric levels cannot be explained solely by geological or chemical reactions. In addition to transit spectroscopy, JWST employs direct imaging to locate planets. Although challenging due to stellar glare, JWST's advanced coronagraphs help block out starlight, making direct observation of planets possible. High-contrast imaging allows JWST to detect planets in habitable zones of nearby stars by capturing their faint reflected or emitted infrared light. These observations verify the planet's existence while providing initial estimates of size, orbit, and atmospheric features. JWST's ability to analyze atmospheres enables scientists to evaluate habitability. For planets in the habitable zone, atmospheric stability and surface conditions are key factors. JWST can detect water vapor, greenhouse gases, and other atmospheric markers that suggest a planet might support life, serving as a sort of health check for planetary environments. Identifying key gases and molecules indicates whether a planet's climate could sustain life. Another advantage of JWST is its capacity to discover planets orbiting faint, distant stars that were previously inaccessible. Its sensitivity allows it to peer deep into the galaxy, uncovering planets around dim or dust-obscured stars. Many of these stars are in young stellar systems or dense galactic regions where earlier telescopes struggled. This broadens the catalogue of exoplanets and increases the chances of finding worlds within the habitable zone that may have Earth-like conditions. Determining a planet's size and composition is essential, and JWST contributes by measuring transit depths across multiple wavelengths. From this data, scientists can infer the planet's radius and estimate its density, which helps distinguish rocky Earth-like worlds from gaseous giants like Jupiter. This distinction is vital because only terrestrial planets with solid surfaces are promising candidates for habitability. These methods work together through an integrated approach, combining JWST data with observations from other telescopes, ground-based and space-based. Such synergy enhances confirmation of planetary candidates, refines atmospheric models, and improves orbit characterizations. This comprehensive analysis helps prioritize targets for future detailed studies, potentially with missions designed explicitly to detect signs of life. In essence, JWST acts as a cosmic detective, uncovering secrets of distant planetary systems. It interprets atmospheric compositions, assesses planetary characteristics, and evaluates potential habitability based on a planet's position relative to its star. Its capabilities broaden our understanding of the universe's vast diversity of worlds and bring us closer to answering whether we are alone. Detailed planetary properties revealed by JWST turn speculation into scientific investigation, making progress toward discovering worlds that may support life. Through its advanced technology, JWST also opens new frontiers in searching for habitable environments beyond our solar system. The atmospheric data it provides help distinguish Earth-like planets from gaseous or inhospitable worlds. Its ability to detect atmospheric gases linked to biological activity could be crucial in identifying signs of life. The search focuses on specific molecules, water vapor, oxygen, methane, that, when in the right balance, suggest possible biological processes. Detecting water, fundamental for life as we know it, is especially significant. JWST's direct imaging capabilities, bolstered by coronagraphs, are particularly promising for nearby stellar systems. By blocking out starlight, scientists can observe planets directly, estimate their sizes, and analyze atmospheric compositions. These direct detection methods complement transit observations, offering a more complete understanding of planetary systems and their habitability potential. Overall, JWST's combination of high-sensitivity spectral analysis and advanced imaging creates a comprehensive approach to exoplanet exploration. These techniques help scientists prioritize the most promising candidates for further investigation, moving us closer to answering profound questions about the universe's habitability. In conclusion, JWST is transforming our understanding of distant worlds. It is a powerful tool for examining planetary atmospheres, assessing habitability, and seeking signs of life. Its innovative capabilities help unravel the mysteries of planets in the habitable zone, expanding the frontiers of space exploration and bringing humanity closer to discovering other potentially life-supporting worlds. The revelations brought forth by the James Webb Space Telescope compel us to reconsider what we once thought we knew about life's place in the universe. As JWST peels back layers of cosmic history, it's revealing environments where conditions might someday support life, or at least make it conceivable that we are not alone in this vast expanse. When we examine the earliest galaxies light years away, we see worlds forming amidst unimaginable energies and chaos. Those nascent galaxies, just a few 100 million years after the Big Bang, hint at a universe where the building blocks of life could have emerged surprisingly early. The discovery of water vapor in the atmospheres of distant exoplanets, some orbiting stars not unlike our Sun, fuels a provocative question. Are we witnessing the initial stages of habitable conditions elsewhere? If water, the essential ingredient for life as we understand it, exists on planets several billion light-years from Earth, it implies that the potential for life might be far more common than previously imagined. The telescope's ability to analyze the atmospheres of distant worlds has opened a corridor into environments that bear striking similarities to Earth's own conditions during its formative years. Gases like methane, oxygen, and carbon dioxide detected in these atmospheres could provide clues about biological processes, or at least prebiotic chemistry, those chemical pathways that could eventually lead to living organisms. While these signs are not direct evidence of life, they act as markers, pointing us toward worlds that might host or have hosted life forms. It feels as though we are slowly assembling a directory of potentially habitable planets scattered across the universe, each one a candidate in the high-stakes game of cosmic possibility. Dark matter and dark energy, which make up the lion's share of the universe's mass-energy budget, may seem removed from the question of life. Yet their influence shapes cosmic evolution, affecting galaxy formation and the distribution of matter in ways that could impact habitability. For example, dark energy drives the accelerated expansion of the universe. Without this mysterious force, the universe's large-scale structure might look very different, and perhaps conditions for life as we know it could have been more or less likely under different circumstances. The universe's vast scale, billions of galaxies, each containing billions of stars and potentially even more planets, suggests a statistical likelihood that environments suitable for life exist somewhere beyond our own cosmic neighbourhood. Given the staggering number of planets orbiting distant stars, the odds tilt in favour of some of those worlds developing life, whether simple microbial organisms or complex intelligent beings. The more we explore, the more it becomes clear that Earth's rarity in the universe is an open question rather than an established fact. Meanwhile, the presence of black holes in galactic centres hints at extreme environments where biology, as we understand it, couldn't survive. Still, their very existence indicates the universe's capacity for extremes, conditions that could be hostile or, intriguingly, could host entirely different forms of life adapted to those worlds. The diversity of environments we're uncovering underscores one profound truth. If life exists elsewhere, it might be unlike anything we've ever imagined, operating under laws or conditions that are alien to our own experiences. All of these findings suggest that the universe is not just vast and old, but also potentially fertile ground for life to emerge. The universe's scale, its complexity, and the abundance of planets and environments echo a silent question. Are we unique, or are we just one of many cosmic experiments in the grand dance of evolution? As JWST continues to piece together these cosmic puzzles, it's impossible not to feel a tantalizing sense of possibility that somewhere among the countless worlds spinning in distant galaxies, life might be waiting, perhaps observing us just as intently as we search for it. The quest to find habitable worlds extends far beyond merely discovering new planets. It's a journey that pushes the boundaries of our understanding about what makes a planet suitable for life, and by extension, what that means within the vast tapestry of the universe. As the James Webb Space Telescope peers into the depths of space, it acts like a cosmic detective, searching for telltale signs that life could potentially exist elsewhere. These investigations are not just about finding alien worlds, they're about understanding our own origins and place in an incomprehensibly large universe. Every potentially habitable planet, each rocky body with an atmosphere, acts as a clue in a grand cosmic puzzle. When JWST examines these planets' atmospheres, analysing the presence of water vapour, oxygen, methane and other molecules, it's akin to taking a snapshot of possible life-supporting ingredients. Think of it like peering into a hidden world, where the conditions for life might be quietly brewing. The more we find that mirror Earth-like conditions, the more it challenges our previous notions that Earth was some rare pearl floating alone in this cosmic sea. Instead, we begin to see that habitable worlds might be more common than we ever dared to believe. This search also underscores the true scale of the universe. The more worlds we examine, the clearer it becomes that our solar system is just a tiny island in an endless ocean of planets and stars. Each new discovery stretches our imagination. Are we truly alone, or is life sprouting in every corner of this immense universe? The sheer number of planets orbiting distant stars, many residing within their star's habitable zone, or Goldilocks zone, hints at the possibility that life could be widespread. It's as though the universe is whispering that the conditions for life might be a common outcome, not a rare accident. Yet, the search for habitable worlds also exposes just how fragile and delicate these planetary environments can be. For every promising candidate, there are countless others where conditions are far from life-friendly, too hot, too cold, lacking atmosphere, or bombarded by cosmic radiation. This contrast helps us appreciate Earth's fragile beauty and delicate balance. It drives home the idea that life's existence depends on a rare confluence of factors, making our own planet a precious jewel in the cosmic expanse. We realize that even in a universe teeming with stars and planets, habitable worlds are precious and perhaps few, which adds to the awe and mystery. Furthermore, the search deepens our understanding of planetary evolution. How do planets develop atmospheres capable of supporting life? What roles do their stars' energy, geological activity, and cosmic environment play? These questions lead us to explore conditions that might foster life in environments vastly different from Earth's. Perhaps life exists in forms we've yet to imagine, thriving under alien skies and in unfamiliar aquatic worlds or subsurface habitats. Each discovery expands our horizons, teaching us that the universe's complexity is greater than simple Earth-centric models could ever suggest. In this grand pursuit, the search for habitable worlds transforms from a mere scientific activity into a profound statement about our universe's vastness and diversity. It reminds us that our planet, while unique and precious, might be only one of countless cradles of life scattered across the cosmos. As the James Webb Space Telescope continues to uncover these distant worlds, it offers not just data but a humbling perspective. Our universe is not only enormous, but also filled with mysteries waiting to be unravelled. And in finding other worlds that could harbour life, we learn more about ourselves, about the uniqueness and fragility of our home planet, and about how awe-inspiringly vast and interconnected the universe truly is. The images and data collected by the James Webb Space Telescope are rewriting our understanding of how the universe originated. For centuries, scientists relied on telescopic observations, models, and physics to piece together cosmic history. But now, JWST's unprecedented infrared sensitivity offers a new window into the earliest moments after the Big Bang, moments previously hidden. One major influence of JWST is in revealing the first galaxies to form after the universe's birth. Before JWST, many believed these primordial structures, known as Population 3 galaxies, might be rare or too faint for detection. Now, JWST's ability to peer through cosmic dust and observe distant, ancient light is uncovering galaxies formed just a few 100 million years post-Big Bang. These discoveries challenge earlier models that suggested galaxy formation was slow, instead indicating that the universe could quickly produce complex star-filled systems. This impacts our understanding of cosmic evolution's timeline. If early galaxies like these were common, it implies mechanisms for rapid star and galaxy formation, possibly involving dark matter halos acting as scaffolding or more efficient cooling processes that enable faster gas cloud collapse. Each new observation pushes the boundaries of how quickly structures assembled, causing scientists to revisit and refine their theories. JWST also sheds light on reionization, a pivotal phase when the universe transitioned from neutral hydrogen to an ionized state, allowing light to travel freely. Previous observations hinted at this epoch, but lacked detailed insight into the sources responsible. Now, by studying distant galaxies' star formation rates, JWST reveals many early galaxies emitted intense radiation capable of reionizing the universe. This supports the idea that numerous small yet plentiful galaxies drove this transformation, rather than a few massive quasars or black holes. Beyond galaxies, JWST's observations of the cosmic microwave background, the faint afterglow of the Big Bang, are fueling discussions about the universe's earliest moments. Tiny fluctuations in this relic radiation contain the seeds for all future structures, galaxies, clusters, and superclusters. Comparing JWST data with these primordial clues helps refine models of cosmic inflation. Rapid expansion, just fractions of a second after the Big Bang. The findings suggest the universe's initial conditions might be more complex than previously thought, with subtle variations in energy fields or unexpected dark energy properties. Another key area of impact is in understanding how heavy elements formed. Elements heavier than hydrogen and helium are synthesized in stellar cores and during supernovae. Observing early star-forming regions, JWST reveals how quickly these metals appeared in the universe. Surprisingly, some data show metal-enriched stars existed soon after the first galaxies formed. This hints that the cycle of star birth and death was more efficient at enriching the cosmos quickly, creating building blocks for planets, and potentially life, faster than earlier models suggested. Perhaps the most exciting promise of JWST is in searching for signs of early life or habitable worlds. By analysing exoplanet atmospheres, JWST seeks biosignatures, gas combinations indicative of life. Detecting such signs in planets formed in the universe's infancy would radically alter our models of life's origins, implying that life could have begun far earlier than previously expected. Throughout all these advances, JWST isn't just peering into the past, it's actively reshaping our theories of cosmic origins. Each new image and data point adds to a growing puzzle, prompting us to reconsider timelines, mechanisms, and foundational processes behind the universe's birth. It reminds us that, in this grand cosmic story, our understanding is still unfolding, yet JWST's gaze brings us closer than ever to uncovering the universe's deepest secrets. Thanks to the James Webb Space Telescope, we've begun to uncover the processes that forge planetary systems and, ultimately, conditions conducive to life. Its incredible infrared sensitivity allows us to peer through dense gas and dust clouds, where stars and planets form, an achievement previously nearly impossible. With JWST, we're studying stellar nurseries in exquisite detail, witnessing the raw materials and dynamic processes that culminate in new worlds. One of the most stunning insights involves protoplanetary disks, vast, swirling collections of dust and gas surrounding young stars. JWST has captured images revealing intricate structures within these disks, such as rings, gaps, and possible planet-forming regions. These features suggest gravitational interactions and accretion processes shaping planets, as if witnessing the cradle of planetary systems unfold before our eyes. This provides direct evidence supporting theories that planets form from leftover material of star formation, gradually building from dust grains that stick together and grow into larger bodies, but contributions extend beyond formation mechanics. By analysing the chemical compositions of these disks, JWST has uncovered complex organic molecules, some of the building blocks of life, forming in environments once thought too harsh or chemically simple. This suggests that life's ingredients may be more common than previously believed, seeding planets with the essentials needed for life to develop. JWST also advances our understanding of exoplanet atmospheres, particularly those in habitable zones. By scrutinising atmospheric spectra, scientists detect water vapour, carbon dioxide, methane, and other gases that could indicate conditions suitable for life. For instance, observations of temperate exoplanets have revealed atmospheric compositions hinting at weather patterns, cloud formation, and chemical processes similar to Earth's. These findings are reshaping our ideas of planetary habitability and the potential for life elsewhere. Remarkably, JWST has begun studying planets in early development stages or in extreme environments. Observations of young, massive planets still heating and assembling provide clues about giant planet formation and evolution. These insights help answer whether our solar system's configuration is a rare coincidence or part of a broader pattern of planetary development across the galaxy. Furthermore, JWST sheds light on how stellar radiation and cosmic environments influence planetary systems. High-energy ultraviolet light from host stars affects atmospheric chemistry, potentially stripping atmospheres or fostering complex molecules. Understanding these interactions helps determine atmospheric longevity and stability, key factors in assessing habitability. Collectively, these discoveries suggest planetary system formation isn't rare or accidental, but a common consequence of stellar evolution. From starbirth remnants to the dance of dust, gas, and gravity, Webb's observations indicate that the universe teems with planets, many on pathways toward habitability. Nature seems to push these cosmic building blocks toward creating environments where life could eventually flourish. JWST insights also challenge previous models of planetary development timing. Observations reveal planets can assemble much faster, within a few million years after star formation, narrowing the timeline for the emergence of life. Habitable conditions might develop quickly after planets are born, accelerating our understanding of when life could arise. By revealing this rich picture of planetary birth and evolution over cosmic time, JWST offers a more complete view of our place in the universe. Words like rare and fortunate gain new meaning as we realize that the ingredients and processes for life are woven into the fabric of the cosmos. Each discovery brings us closer to answering whether we are alone or whether the seeds of life are scattered throughout the universe, waiting to bloom on distant worlds. The more we learn, the clearer it becomes. Life's potential is rooted in the very processes JWST is unveiling. This journey of discovery is just beginning, and each day brings new doors to understanding not just how planets and life form, but how extraordinary the universe truly is. When we peel back the layers of cosmic history and glimpse the universe's origins, everything we believed about our place in the grand tapestry shifts dramatically. The insights provided by the James Webb Space Telescope pull back the curtain on the earliest moments of existence, moments when the universe was a swirling mass of particles, energy, and potential. It's as if we are standing at the edge of an infinite timeline, watching the first sparks of galaxies, stars, and planets ignite across the vast darkness. This understanding shakes loose the notion that humanity is the center or the pinnacle of existence. Instead, it paints a picture of a universe that is both unimaginably old and perpetually evolving. It's a reminder that our tiny blue planet, though precious to us, is just one flickering point in a cosmic ocean that spans billions of light years. Recognizing that the universe is over 14 billion years old makes our few thousand years of recorded history seem like a single heartbeat in the grand rhythm of cosmic time. We aren't the masters of the universe. We are a fleeting consciousness born from its intricate processes. Knowing how the universe began, from the Big Bang to the formation of the first galaxies, gives us a sense of humility and wonder. It reveals that the laws of physics and chemistry, the very building blocks of existence, have been in play since those earliest moments. It's extraordinary to think that the atoms in our bodies originate from the ashes of ancient stars that exploded long before humanity ever existed. The iron in our blood, the calcium in our bones, and the carbon that makes up all life as we know it were forged in the hearts of long-dead stars, and scattered across the universe in supernovae. This cosmic perspective fosters a deep sense of interconnectedness. We are not separate from the universe. We are woven into its fabric. Every breath we take, every molecule in our bodies traces back to the universe's fiery beginnings. That realization sparks a profound sense of stewardship and curiosity. If we are part of this vast, interconnected cosmos, then understanding our origins becomes an imperative, not just for science, but for our collective future. Moreover, these revelations ignite our curiosity about the potential for other forms of life. If the universe's origins led to the formation of planets and stars, then maybe, just maybe, similar pathways could have sparked life elsewhere. The discovery of ancient galaxies and exoplanet atmospheres by JWST hints at the possibility that conditions for life might be more common than we previously thought. That realization rewrites our understanding of our uniqueness. It opens doors to questions about whether we are truly alone, and if life might be fluttering somewhere among the stars. Seeing how the universe evolved also prompts us to consider the fragility of our existence. The universe's early chaos, with its violent collisions and tumultuous formations, was a crucible that ultimately brought about the stable cosmos we inhabit today. Our very existence rests on a narrow set of circumstances, a cosmic coincidence that allowed life to flourish on Earth. That makes each moment of life precious, each discovery a gift, a reminder that we are part of something delicate and extraordinary. Holding these cosmic truths, we gain a humbling perspective. We are simply visitors in this universe, brief but significant in our awareness of it. Our brief sparks of consciousness, our hopes and dreams, are echoes of the universe's own long unfolding story. Through understanding the universe's origins, we find ourselves not separate from it, but as active participants in its ongoing creation, cosmic explorers charting their place within the vast, terrifying, and beautiful universe. As we peer further into the universe than ever before, JWST's revelations challenge both our scientific understanding and fundamental philosophy. The cosmos's astonishing scale, unveiled through JWST's observations, prompts profound questions about our place, existence, and life's meaning, asking us to reconsider long-held assumptions. One key philosophical question concerns our position within this vast universe. Historically, humans viewed Earth as central or special in a grand design. But as telescopes improved, it became clear Earth is just a tiny speck among countless galaxies. JWST's ability to observe ancient galaxies and the universe's earliest structures emphasizes both our insignificance and potential importance. Is humanity alone? If billions of galaxies contain billions of stars and planets, does that diminish or amplify our significance? These questions challenge us to consider whether meaning is imposed by humans or is an intrinsic part of an indifferent universe. The notion of cosmic insignificance underscores existential dilemmas. Are we a fleeting moment amidst an expanding universe? JWST's insights into the universe's age, billions of years of evolution, and the countless galaxies predating our solar system highlight a universe that doesn't revolve around us. Yet, does this vast indifference undermine life's value or make it more precious? Might our existence amid this infinite cosmos create a sense of responsibility? These questions have ethical implications. What moral obligations do we hold? Are we merely custodians of a fragile planet or temporary inhabitants destined to fade like the ancient galaxies JWST reveals? Another fundamental question relates to destiny and free will. If the universe operates under unchangeable physical laws, what does that say about human agency? Are our choices the result of complex physical processes dictated by initial conditions laid out billions of years ago? Or is there space for genuine free will within cosmic determinism? Knowing the universe's distant past suggests the future may be similarly preordained. Yet human curiosity and exploration, embodied by JWST, may transcend these boundaries, allowing us to carve meaning through knowledge and discovery. JWST's potential detection of life on distant exoplanets intensifies these philosophical debates. If signs of habitability or life are found elsewhere, how does that affect our understanding of consciousness and its origins? Is life a rare accident or an inevitable cosmic pattern? If life exists beyond Earth, questions of spiritual significance and purpose arise anew. Do other worlds harbour their own consciousness or moral frameworks? These considerations force us to confront what it means to be alive and conscious and whether life on Earth is a unique miracle or part of a universal pattern. The vast scale of the cosmos prompts reflection on time and eternity. JWST's ability to look back to the universe's infancy invites speculation about an eternal universe undergoing cycles of creation, destruction, and rebirth. What does this imply for individual consciousness or human history? Are our fleeting joys, sufferings, and achievements meaningful within the broader cosmic context? Or are they insignificant blips in an endless dance? If the universe will expand forever into a cold, silent void, what is the fate of existence itself? On a meta-level, JWST's discoveries challenge our epistemological assumptions, what we can know and the limits of human understanding. The universe's vastness suggests some truths may be forever beyond our grasp, shrouded in cosmic mysteries. How do we reconcile our desire for knowledge with the possibility that some aspects are fundamentally unknowable? Is our pursuit noble or futile in the face of infinite complexity? These questions remind us that, despite our curiosity, the universe may remain an eternal mystery. Contemplating the universe's scale and JWST's insights, we confront our longing for meaning, connection, and understanding. Our knowledge is deepened, yet these revelations also lead us to reflect on whether our purpose is encoded in the stars or something we create ourselves amid the cosmic silence. The telescope's gaze becomes a mirror, reflecting our hopes and fears. It prompts us to ask whether the universe is a cold, indifferent expanse or a vast sanctuary filled with purpose awaiting discovery. As JWST unveils more secrets, we feel both humbled and inspired, driven to seek meaning amid the infinite, to cherish fleeting moments of clarity and connection within our brief existence in this awe-inspiring cosmos. As we gaze into the depths revealed by the James Webb Space Telescope, it's impossible not to feel a mix of wonder and an almost visceral sense of fear. These discoveries thrust us into a realm where the vastness of the universe is no longer just a distant concept, but a tangible, almost overwhelming reality. Each new image of ancient galaxies, some formed just a few 100 million years after the Big Bang, serves as a stark reminder that our universe is unimaginably old and vast beyond ordinary comprehension. They force us to confront how tiny and fleeting our existence is in the grand cosmic scale, yet simultaneously ignite a deep curiosity about our origins and purpose. The discovery of ancient galaxies, millions or even billions of light years away, shatters prior notions of the universe's timeline and pushes us into the terrifying realization of how much we have yet to understand. When we look at these galaxies, we essentially look back in time, seeing the universe as it was when it was still young. This idea alone is almost surreal. We are examining relics of an unfathomably distant past, and those relics hold clues to the formation and evolution of cosmic structures. What's truly humbling is realizing that the light reaching us now has traveled for eons, crossing distances so immense that our daily human scale seems insignificant in comparison. But alongside awe, there's a creeping sense of unease. These observations are unsettling because they hint at how fragile and rare life might be in such an immense universe. As we find more exoplanets with signs of potential habitability, an eerie question arises: are we truly alone? The universe's sheer scale means that the chances of other life, intelligent or otherwise, are both high and terrifying to contemplate. The universe's vastness suggests that life could be out there, scattered across unthinkable distances, living on worlds that we may never reach or even comprehend. In this light, Earth's unique biosphere feels both precious and terrifyingly fragile, still a tiny island amid an ocean of darkness. The universe's scale is also exemplified by the black holes and dark matter that JWST continues to uncover. Black holes, specifically supermassive ones lurking at galaxy centers, remind us that even the most massive objects are but tiny points in a universe filled with phenomena that dwarf human understanding. Their existence hints at destructive forces capable of swallowing entire star systems, fueling fears about the destructive potential of cosmic entities. Meanwhile, dark matter, an invisible component making up most of the universe's mass, forms a mysterious scaffold holding galaxies together. Its elusive nature fuels the unsettling reality that much of the universe remains hidden and unknowable, shrouded in darkness that we can only detect indirectly. The more the JWST reveals, the more the universe exemplifies a terrifying scale of existence that far surpasses our ancient stories and philosophies. It's a universe that stretches the limits of human imagination, where galaxies collide, black holes devour stars, and dark matter drapes everything in unseen forces. It challenges our sense of significance and makes clear how insignificant and vulnerable we are amid the cosmic ballet. Yet, rather than diminishment, this realization fuels a fiery curiosity, the urge to understand, explore, and push the boundaries of what we know. It's a call to action, feeling the universe's terrifying grand scale not as a source of despair, but as a testament to our relentless spirit of discovery and the unyielding hope that among all that darkness, we might find a flicker of understanding or even a sign of life beyond our tiny blue planet. The James Webb Space Telescope's discoveries mark a new era in space exploration, revealing insights into the universe's infancy, complex structures, and exoplanet atmospheres. These revelations prompt a shift toward building next-generation telescopes that extend our reach further into cosmic history. Following JWST's success with multi-wavelength, high-resolution observations, efforts are underway to develop even more powerful instruments, both ground-based and space-bound, that can probe deeper into the universe's origins, approaching the time of the Big Bang. Projects like the Nancy Grace Roman Space Telescope will complement JWST by mapping large sky areas with unprecedented accuracy, helping to understand dark energy's role in cosmic expansion. Simultaneously, extremely large ground-based telescopes with hundreds of feet-wide mirrors will explore faint galaxies, probe dark matter, and study exoplanets in greater detail. Technological advancement isn't limited to building larger telescopes. Improving data analysis capabilities is equally vital. The vast amount of data collected demands sophisticated algorithms, artificial intelligence, and machine learning to process cosmic signals efficiently. These tools help identify patterns, detect subtle phenomena, and generate new insights into the universe's complex structure. International collaboration is increasingly central to future missions. Space exploration has always been a global endeavour, and JWST's discoveries underscore the importance of pooling resources and expertise. Future collaborations will likely involve shared data, coordinated observations across multiple platforms, and international partnerships that accelerate discovery, reduce costs, and foster a collective curiosity about the universe. Beyond observation, strategic efforts aim to push human presence beyond Earth. The Moon's south pole, rich in water ice and stable for long-term bases, is seen as a crucial staging ground for deep space missions. Knowledge gained from JWST about planetary formation, atmospheres, and the universe's origins will inform mission designs, preparing us for human exploration of distant worlds. Mars, already a target of robotic missions, could become a hub for scientific research and potential colonization, as understanding of exoplanet atmospheres and early galaxies improves. Understanding our cosmic origins will also benefit from continuous refinement of theoretical models based on JWST's findings. Observing the earliest galaxies, star populations, and primordial gas clouds helps reconstruct how the universe evolved from a uniform plasma into today's structured cosmos. This iterative feedback loop between observation and theory will lead to more accurate simulations of cosmic evolution, guiding further exploration efforts. The search for extraterrestrial life is another crucial pursuit. JWST's capacity to analyze exoplanet atmospheres for biosignatures sets the stage for targeted missions to find habitable worlds. Missions like ESA's Ariel and future flagship telescopes aim to identify planets with conditions suitable for life, bringing us closer to answering whether we are alone. JWST's findings will help refine the criteria for habitable planets, sharpening future searches for life beyond Earth. Inspiring new generations remains integral to the ongoing journey. JWST's awe-inspiring images and discoveries rekindle curiosity and passion, emphasizing that space exploration is a human story that continues to evolve. Developing new tools, expanding collaborations, and reaching further into the cosmos will sustain this spirit of discovery. As our understanding deepens, so too does our capacity to explore and learn from the universe. The universe's vastness, once a barrier, now serves as a beckoning call. The next steps involve a harmony of technological innovation, global cooperation, theoretical advancement, and relentless curiosity. With each discovery, we unravel more of the universe's secrets, transforming it from an incomprehensible frontier into a realm of understanding. JWST has illuminated just a fraction of its depths, igniting a collective drive to explore further, deeper, and with bolder visions. The journey has only just begun. As we marvel at the James Webb Space Telescope's groundbreaking discoveries, it's natural to wonder what lies ahead. JWST has opened a new chapter in cosmic exploration, but it's only the beginning. Future telescopes and missions will build upon these revelations, peeling back more layers of the universe's profound mysteries. One promising avenue is developing next-generation space telescopes with even greater sensitivity and resolution. Imagine telescopes with larger mirrors, advanced detectors, and cutting-edge technologies capable of observing fainter objects across wider spectral ranges. These instruments could peer deeper into the universe's infancy, detecting galaxies and stars so ancient they form the first light after the Big Bang. They might even reveal population 3 stars, the universe's first luminaries, long hidden in cosmic shadows. Building on JWST's success in characterizing exoplanet atmospheres, future missions could focus on finding potentially habitable worlds in nearby star systems with unprecedented precision. Telescopes designed to directly image Earth-sized planets within habitable zones could analyze atmospheric compositions for signs of life. Incorporating advanced coronagraphs and starshades would block stellar glare, allowing clear images of distant planets. Such missions could answer whether life exists beyond Earth, transforming speculation into concrete discovery. Beyond visible and infrared wavelengths, upcoming observatories might explore ultraviolet X-ray or gamma-ray ranges. High-energy observations could reveal explosive phenomena like supermassive black hole jets or gamma-ray bursts, shedding light on the universe's most energetic events. These observations may also help us understand dark matter's elusive nature through gravitational effects detectable only in high-energy astronomy. In addition to more advanced telescopes, new space missions will include innovative technologies like interferometry, combining signals from multiple telescopes to create a virtual, colossal instrument. Space-based interferometers could achieve sprawling baselines, offering angular resolutions capable of resolving details impossible for single telescopes. This approach might revolutionize our understanding of stellar nurseries, planetary system formation, and intricate structures within distant galaxies. Another frontier is large-scale sky survey projects, designed to map vast regions systematically. These surveys could uncover transient phenomena like fast radio bursts, pulsars, or signals from the early universe that flicker and fade in seconds or minutes. Such comprehensive mapping would generate detailed cosmic census data, charting the distribution of galaxies, dark matter, and voids with greater accuracy. This data will refine models of cosmic evolution, revealing patterns and anomalies challenging current theories. On the technological front, future missions are likely to incorporate artificial intelligence and machine learning algorithms to manage the vast data volumes collected. These tools could automatically identify unusual objects or phenomena, directing scientists toward unexpected discoveries. As observational capacity grows exponentially, these capabilities will be crucial in ensuring no cosmic secrets remain hidden in this ocean of data. The quest to understand the universe's true scale will also foster international collaborations on even more ambitious projects. Countries worldwide are pooling resources to develop observatories like the European Space Agency's Athena X-ray Observatory and the proposed LUVOIR, Large UV Optical Infrared Surveyor. Such collaborations push scientific boundaries, combining technological strengths and perspectives to unlock cosmic secrets. While JWST has already transformed our perspective, future missions promise a cascade of discoveries that could redefine our understanding of reality. We may find evidence of extraterrestrial civilizations, unravel the true nature of dark energy driving cosmic acceleration, or glimpse phenomena yet to be imagined. Each new mission builds on the last, creating a relentless march of progress fueled by curiosity, technological innovation, and our desire to comprehend the universe's vastness. Throughout this journey, we will confront the universe's breathtaking truth, that it is not only immense but also profoundly mysterious, a place challenging our perceptions and urging us to think beyond what's visible. It pushes us to embrace the wonder of the unknown. From JWST's discoveries to future explorations, each step demonstrates humanity's unending quest to understand our place among the stars and perhaps our role in the grand cosmic story. The future of the James Webb Space Telescope promises numerous technological and scientific advancements that could reshape our understanding of the cosmos. As JWST explores deeper space, its innovations will enable discoveries that may unravel profound mysteries of the universe and push engineering boundaries. A particularly exciting prospect is refining our knowledge of exoplanets. JWST's ability to analyze atmospheres of distant worlds could revolutionize the search for extraterrestrial life. Detecting molecules such as water vapor, methane, or oxygen might identify potentially habitable planets. As technology advances, future telescopes could perform even more detailed spectroscopy, revealing biological or prebiotic chemical signatures. Understanding exoplanet atmospheres, climates, and their capacity to support life will be central to this effort. On the technological side, improvements in detector sensitivity and data processing will continue to accelerate. The vast data collected by JWST requires advanced machine learning and artificial intelligence to analyze efficiently. These tools will help identify phenomena like supernovae, gravitational lensing, or fast radio bursts more quickly and accurately. Integrating AI into space missions could enable real-time observation adjustments, optimizing data collection and ensuring no critical moments are missed. Enhancements in mirror fabrication and cooling technologies will pave the way for more powerful future space telescopes. JWST's segmented, gold-coated mirror demonstrates the potential for larger, more sophisticated arrays capable of operating at longer wavelengths with higher resolution. Future telescopes could be as large as a kilometre across, orbiting far beyond Earth's atmosphere. They might directly image Earth-like exoplanets, analysing surface features, cloud cover, and seasonal changes. Scientifically, our understanding of the universe's remaining mysteries will deepen. Dark matter and dark energy, comprising about 95% of the universe's total mass energy, are key areas where JWST's observations could provide critical insights. These data might help constrain theories about their nature, potentially revealing new physics or exotic particles. Combining JWST findings with particle physics experiments could lead to breakthroughs, shedding light on the universe's fundamental structure. The detection of gravitational waves by observatories like LIGO and Virgo opened a new window into the cosmos. With enhanced coordination between space and ground-based observatories, multi-messenger astronomy will grow more powerful. This approach allows detailed studies of violent events like neutron star mergers, helping us understand the origin of heavy elements and the formation of black holes and neutron stars. Observing these phenomena across electromagnetic and gravitational wave spectra will offer unprecedented insights. Exploring cosmic origins remains a key focus. JWST's ability to look into the universe's earliest epochs enables studying the formation of the first stars and galaxies. Future telescopes will build on this, tracing back to the coalescence of primordial gas clouds and dark matter's role in structure formation. These efforts will deepen our understanding of cosmic history, potentially explaining why the universe appears fine-tuned for life. They might even reveal clues about multiverses or alternate realities. Beyond pure science, technological innovations driven by JWST and its successors will impact many sectors. Advances in data compression, lightweight materials and cooling systems could influence computing, aerospace, and other industries. Building instruments for extreme space conditions pushes technological limits, often resulting in innovations that benefit terrestrial applications. All these advancements highlight human curiosity and ingenuity. Each new discovery prompts further questions, fueling ongoing exploration and technological progress. The universe is a vast, complex puzzle, filled with endless pieces waiting to be uncovered, each piece revealing how wondrous, terrifying, and humbling our cosmos truly is. As we approach these future breakthroughs, one truth remains clear. The universe holds many secrets, and JWST is only beginning to unveil its deepest mysteries. This endeavour is about uncovering our origins, understanding matter and energy, and exploring the potential for life beyond Earth. As JWST continues its mission, its impact will extend far beyond astronomy, inspiring innovations across industries and advancing our quest to comprehend the universe's grand design. The coming decades promise transformations in our understanding of the cosmos, driven by relentless pursuit of knowledge that defines humanity. As we stretch the boundaries of our view, peering deeper into space, we can't help but feel humbled and awed by what lies beyond. Each new discovery, each pixel of ancient light, challenges our notions of smallness and our place in the cosmic tapestry. The universe is not just bigger than imagined, it's almost unfathomably vast, with scales beyond human comprehension. This expansion compels us to confront profound questions. What does it mean to be human in a universe where galaxies are separated by distances so vast that even light takes millions or billions of years to travel between them? Observing early galaxies, born when the universe was just a fraction of its current age, also shakes our understanding of time and origin. Our solar system and Earth are tiny specks in this cosmic ocean, standing on the edge of a staggering abyss and gazing into eternity. This realization inspires perspective. It diminishes illusions of importance that often dominate daily life, replacing them with recognition of our fragile, fleeting existence within an endless universe. The universe doesn't revolve around us. Instead, we are part of an intricate web of cosmic phenomena unfolding over eons. The more we learn, the more we see how transient and rare our existence may be. This can evoke feelings of insignificance and privilege, insignificance in the cosmic scale, yet privilege to be conscious observers capable of understanding it. Contemplating a universe so vast and ancient invites deep, philosophical reflection on our purpose. If galaxies and stars form and die over billions of years, what significance can we assign to human life? Is our search for meaning a product of chance, or is there something more to discover amid the cosmic dark? Does understanding the universe's scale diminish or deepen our quest for meaning? These questions shake foundational philosophical views, challenging us to reconsider our relationship with existence itself. At the same time, the expanding universe emphasizes interconnectedness. Every atom in us was once part of ancient stars that exploded in distant galaxies. Looking across billions of light years, we see that we are, in a literal sense, made of stardust. This realization shifts our perspective from separation to unity, reminding us that boundaries we draw between ourselves and the cosmos